Welcome, dear listener, to The Sleepy Scientist. This is your time to rest, to breathe, and to let your mind drift gently as you settle into the quiet of the evening. Tonight's journey takes us far back in time to an Earth that looked nothing like the calm blue planet we know today. Long before oceans, trees, or even continents, our world was a restless ocean of fire. The surface boiled with molten rock, the air shimmered with choking gases, and the skies glowed red beneath a young and violent sun. It was a world of lava, and somehow from that chaos came the beginnings of everything we now call home. Before we set out, I'd love to know, where in the world are you listening from tonight? Perhaps you're curled up in bed in a quiet corner of the city, or maybe you're drifting off in the countryside where the night sky still glows with stars. If you enjoy these journeys into science and wonder, do consider giving the video a like and subscribing. It helps the channel more than you might imagine. And to all of you who are already subscribed, thank you. Your support keeps these stories flowing, and as always, I hope this video isn't so interesting that it keeps you awake. But if it does, at least you'll slip into dreams knowing a little more about the fiery origins of our planet. So let us begin. Picture the Earth not as the blue marble we see from space, but as a glowing sphere of molten rock. A place where the ground was liquid and the sky burned with smoke. What would it have been like to stand on such a world? And how did such a hellish beginning give rise to the seas, the skies, and eventually to life itself? The Earth you know now, with its oceans, forests, and continents, was born out of fire. To understand how it came to be, we need to travel back more than 4 billion years into a time when the solar system was still raw and unfinished. Imagine a sky crowded not with stars alone, but with debris, planetesimals, asteroids, and stray comets swirling around the newborn sun. These fragments, left over from the solar system's construction, were constantly colliding, fusing, and reshaping themselves into the first planets. Earth was one of those lucky survivors, though lucky is a relative term when luck means being struck by countless fiery bodies, each impact releasing unimaginable heat. The planet grew larger with every collision, and that growth came with a price. The surface melted into a global ocean of lava, an ever-churning sea of molten stone. In this glowing infancy there was no stable ground, no continents to stand upon, and no oceans to swim in. The entire surface was fluid rock, reshaping itself from moment to moment. Above it all hung an atmosphere thick with vaporized minerals and gases, sulfur, carbon dioxide, water vapor, and methane, painting the sky in shifting shades of red and grey. The sun, dimmer than today, would have been veiled behind curtains of smoke, casting a strange and ominous light on the roiling world below. And yet, within this fiery chaos, the foundations for everything to come were being laid. Minerals were forming, the chemical seeds of oceans and eventually life itself were already present. And the moon, Earth's constant companion, was soon to arrive through a cataclysmic collision that would change everything. This is the paradox at the heart of Earth's story. The very violence that made it a world of fire also set the stage for it to become a world of water, a cradle for life. To trace this transformation is to understand not only how our planet formed, but why it is so different from our neighbours like Venus and Mars. So in this journey, we will wander through Earth's first moments, its fiery collisions, its molten seas, its toxic skies, and follow the long, slow cooling that brought the first rains, the first oceans, and eventually the first sparks of life. We will compare Earth's fate with that of other planets, explore how we know what the ancient world was like, and reflect on the strange truth that we are only here because our planet was once an inferno. As you listen, let your mind drift with these images. Think of Earth not as fixed and solid, but as a living story, one that began in fire and still carries echoes of that youth deep within its molten heart. For even now, beneath your feet, The core of the planet glows with the same heat that once covered it entirely. And so the question arises, how does a planet survive its own fire, and how did Earth turn a sea of lava into the seas of life? In the beginning, before there was an Earth to stand upon, before there were oceans to sail or mountains to climb, there was only a cloud. Not a cloud like the ones you see drifting across the sky, but a vast cosmic mist, stretching across light years of space. It was thin, cold and silent, made of the scattered remains of older stars that had lived and died long before the sun was born. Within it were the raw ingredients of everything, hydrogen and helium left from the Big Bang, and heavier elements like carbon, oxygen, silicon, and iron forged in the fiery deaths of ancient suns. Astronomers call this the solar nebula, a swirling, slowly collapsing cloud that would one day ignite into the sun and gather together the planets. It may not sound like much, dust floating in the dark, but this dust was extraordinary. Each tiny grain carried the memory of cosmic history. Some were remnants of supernova explosions, others had condensed in the winds of red giant stars, and all of them were drifting, waiting like seeds in the night. The solar nebula was not static. Gravity, the patient sculptor of the cosmos, began to pull it inward. What had once been a quiet cloud started to contract, and as it did, began to spin. Much like a figure skater pulling in their arms to spin faster, the collapsing nebula quickened its rotation. A flat, spinning disk formed, with most of the mass concentrating at the centre. That central bulge would become the sun, a star still in the making, while the outer reaches of the disk carried the leftover material that would one day coalesce into worlds. Imagine it, a vast pancake of gas and dust stretching billions of kilometres across, glowing faintly as heat built up from friction and collapse. At the centre, the sun's fusion had not yet begun, but the pressure was mounting. Once it did ignite, it would blaze with light and energy, sweeping through the disk and altering everything around it. But before that moment, the edges of the disk were a laboratory of creation. Within this cosmic workshop, particles of dust collided and stuck together. At first, these were only tiny clumps, no bigger than grains of sand, but collisions were constant, and sticking together made them stronger. Over thousands, then millions of years, they grew into pebbles, then boulders, and eventually planetesimals, mountain-sized bodies that drifted like silent ships through the newborn solar system. Their gravity pulled in more material, and when they struck one another, they released enormous amounts of heat. The process was violent and chaotic, but it was also how planets are made. Not all the material became planets, of course. Some of it remained as asteroids, comets, and meteoroids, wandering remnants of that early construction project. But within this swirl of matter, Earth was beginning to take shape. The elements that make up the ground beneath your feet, the oxygen in your lungs, and even the calcium in your bones were already present, drifting in that nebula, waiting to be assembled. The recipe for Earth was complex but not random. At different distances from the sun, different substances could survive. Close in, where temperatures were high, only metals and rocky minerals could withstand the heat, which is why the inner planets, Mercury, Venus, Earth and Mars, are all rocky worlds. Farther out, beyond the so-called frost line, it was cold enough for ices and gases to remain, giving rise to the gas giants Jupiter and Saturn, and the icy worlds Uranus and Neptune. Earth's position placed it in the perfect zone for a rocky composition, with the potential to one day hold liquid water. The dust in the nebula was more than just dull grains. Some particles carried carbon-rich compounds, including simple organic molecules. Others contained tiny bits of water ice. These specks were the building blocks of chemistry, the first hints that one day, in the far future, the planet forming from them could support something as complex as life. It is humbling to think that long before oceans rolled or forests grew, the ingredients for living things were floating, silent and invisible, waiting in that cosmic cloud. As the sun finally ignited, its newborn light and solar winds swept through the disk. Much of the lighter gas was blown outward, especially in the inner regions, but the heavier dust and rock remained. These survivors continued clumping, their collisions shaping ever larger bodies. The early solar system would have been a dangerous place, full of impacts and heat, but every collision was a step towards creation. Eventually, through countless mergers and rearrangements, the collection of planetesimals in Earth's orbit grew into a single dominant body. That body would continue to be struck by other large objects, adding to its mass and heating its surface until it was molten. But even in its earliest, most chaotic stages, the Earth to be was already defined by the elements gathered from the nebula. Consider what this means. The iron in the Earth's core was forged in the heart of long-dead stars. The silicon that makes up so much of the crust was born in stellar furnaces. The oxygen that fills our atmosphere began as atoms drifting freely in space, condensed into grains and later locked into minerals. When you look at the Earth, you are quite literally looking at stardust that has been recycled, compressed, and remade into a planet. The solar nebula eventually dissipated, swept clean by the sun's radiation and winds. What remained were the planets, moons, asteroids, and comets we know today. But in that earlier time, the nebula was a nursery cradling the beginnings of worlds. To imagine it is to picture a cloud that was never meant to stay a cloud, but to become something greater. Stars burning with light and planets circling them, waiting for stories to unfold. It is easy to think of Earth as solid and unchanging, but its roots lie in something delicate and fleeting. A drifting cloud of dust and gas, fragile as a wisp of smoke, yet holding within it the power to ignite stars and forge entire worlds. From that gentle beginning, the stage was set for a planet that would one day carry oceans, forests, and perhaps most remarkable of all, listeners like you. And so, before Earth was ever a ball of fire or a home of seas, it was a cloud of dust in the quiet dark. A cloud that carried within it the promise of a world. The cloud of dust that once drifted through space did not stay as dust for long. Gravity, ever patient, was at work pulling clumps of matter together. What began as tiny grains of stardust grew into pebbles, then boulders, and eventually hulking planetesimals, proto-worlds large enough to tug at one another with their own miniature gravity. These wandering bodies orbited the young sun like a bustling crowd of dancers, each crossing path ending in a collision that reshaped them. The process was not peaceful. Imagine millions of rocky fragments hurtling around the solar system at incredible speeds, crashing into each other with the energy of countless nuclear bombs. When two planetesimals struck, the force of the impact melted rock, vaporized minerals, and splashed molten fragments back into space. Some of those fragments would fall back to the growing bodies, welding them larger and stronger. Others were lost, scattered across the void, never to return. This was the environment in which the Earth began to take form. Over millions of years, these collisions produced larger and larger bodies. Small ones were shattered by impacts, while the more massive survivors absorbed their neighbours. Slowly, a few dominant worlds emerged from chaos. Among them, one in particular was steadily gathering mass, the Proto-Earth. Each collision made it grow, each impact heating it until its surface glowed. It is no exaggeration to say that our planet was forged in fire, a body born of relentless cosmic bombardment. If you are picturing this as something graceful, you might need to adjust the image. Accretion is less like a carefully choreographed dance, and more like a cosmic demolition derby. Rocks and molten debris smashed together in every direction. Astronomers sometimes describe it as a snowball fight, but that undersells the drama. It was more like a snowball fight where every snowball explodes on impact, melts into lava, and sticks to its target. A snowball fight with lava instead of snow. Messy, chaotic, and surprisingly effective at building planets. With each new merger, the Proto-Earth grew heavier, and gravity tightened its grip. This growing pull drew in even more wandering planetesimals, accelerating the process. The larger the Earth became, the more it attracted, and the more it attracted, the larger it became. It was a self-feeding cycle. a runaway growth that transformed scattered debris into a world. The energy released during these impacts was staggering. Every collision converted the kinetic energy of motion into heat. With so many high-speed impacts, the surface of the young Earth became an ocean of molten rock. The entire crust melted, glowing like a vast ember in the darkness of space. Scientists call this state a magma ocean, a world where the distinction between land and lava no longer existed. To stand anywhere near it, if standing were even possible, would be to face a horizon of fire stretching endlessly in every direction. As Earth grew, its interior began to separate into layers. Heavier elements like iron and nickel sank toward the centre, forming the core, while lighter silicates floated toward the surface to make up the mantle and crust. This process, called differentiation, created the foundation of the planet's structure. It also generated even more heat, as the movement of dense materials released gravitational energy. Between the bombardments, radioactive decay, and the settling of the core, the young Earth was kept in a near-constant state of molten upheaval. While this fiery birth may sound hostile, it was also crucial. Without these collisions, Earth would never have grown large enough to hold onto an atmosphere or sustain liquid water later on. The impacts that melted the surface also mixed the ingredients of the planet, ensuring the distribution of metals, minerals, and volatiles. In a sense, the violence of the accretion process was a form of cosmic preparation, shaping a world ready to host more complex stories in the ages to come. Even as Earth grew stronger, the collisions did not cease. Some impacts were so large they nearly tore the planet apart. One day, a Mars-sized body named Theia is thought to have collided with Earth, blasting molten rock into orbit and giving birth to the Moon. That particular story deserves its own telling, but it illustrates the scale of events during this chaotic era. Earth's growth was not a gentle accumulation of dust, but a series of titanic impacts that would have been visible across the newborn solar system. The violence of this era is difficult to comprehend. Each impact released more energy than the asteroid strike that ended the age of dinosaurs billions of years later. The difference is that in those early days, such impacts were not the exception, they were the rule. The surface never had time to cool completely before being struck again, reheating the crust, reshaping the terrain, and keeping the planet locked in its molten state. Amid this chaos, the sun was maturing, burning brighter and releasing streams of charged particles that swept across the disk. These solar winds stripped away much of the lighter gases from the inner solar system, leaving behind the denser materials that would define rocky planets. In this way, Earth's fiery accretion was not only about collisions, but also about surviving the sun's early storms. The story of Earth's accretion is one of paradox. It was a destructive process that created. Each impact obliterated whatever came before, but the fragments combined into something new, something larger, something enduring. The Earth you know today, with its mountains, oceans, and fields, grew from countless such destructions, each one a small death that contributed to a greater life. It is worth pausing to consider what this would have looked like to an outside observer. Imagine standing on a nearby planetesimal, watching the proto-Earth glow in the distance. You would have seen a sphere wrapped in fire, impacts flaring like sparks as new material fell in. With every strike, molten rock splashed skyward, glowing arcs of liquid stone tracing across the void. It would have been beautiful in a way that defies imagination, a vision of creation that was at once terrifying and awe-inspiring. Over time, as the number of wandering planetesimals dwindled, Earth's growth slowed. The major accretionary phase eventually came to an end, leaving behind a planet that was larger, hotter, and more complex than before. Though the bombardments would continue for millions of years, the foundations of a world had been laid. Earth was no longer a cloud of dust nor a scattering of rocks, but a single growing body with its own destiny. From dust to planetesimals, from planetesimals to a molten sphere, the path of Earth's creation was guided by fire. The relentless impacts that once threatened to shatter it only made it stronger. And while it is easy to think of Earth as solid and safe, its origins remind us that it is built on chaos. The ground beneath your feet was forged in collisions so violent they melted rock. Yet from that violent beginning rose the stable world that now supports oceans, forests, and life. The accretion of Earth was a cosmic construction project unlike any other, carried out not with tools or plans, but with gravity, chaos, and fire. It was noisy, brutal, and relentless. And yet, in its aftermath, a planet emerged. A world destined in time to turn from fire to water, and from molten chaos to the cradle of life. Imagine standing on the surface of the early Earth, if such a thing were possible. You would not find solid ground beneath your feet. Instead, you would be greeted by an endless heaving expanse of molten rock stretching in every direction like an ocean of fire. Waves of glowing orange and red magma would rise and fall, currents of molten stone swirling and colliding with one another. The horizon would shimmer with heat, and the air would be thick with smoke, gases, and the glow of a world that had not yet cooled into something stable. Scientists call this state the magma ocean, and it is one of the most extraordinary chapters in Earth's history. The young planet had been pummeled by collisions, each impactor releasing so much energy that the crust melted again and again. Eventually, the impacts became so frequent and so powerful that the entire planet's surface was reduced to a global sea of lava. Rather than scattered volcanoes or isolated flows, the whole Earth was itself a volcano, its outer shell nothing more than molten rock in constant motion. To grasp what such a place would look like, it helps to think of modern volcanoes. Consider the glowing rivers of lava flowing from Kilauea in Hawaii, or the fountains of molten rock spraying skyward in Iceland during an eruption. Now take those scenes and expand them to cover the entire globe. There were no islands of safety, no patches of cool rock to cling to, only a restless surface where temperatures soared well above 1,000 degrees Celsius. The appearance of this world would have been surreal. From orbit, Earth would not have been the familiar blue marble, but a glowing sphere pulsing with the light of liquid rock. The colours would shift from deep reds to bright yellows, with darker crusts forming temporarily before sinking back beneath the molten waves. The atmosphere, thick with volcanic gases and vaporized rock, would blur the view, creating a hazy shroud that glowed with reflected fire. What would it have sounded like? A magma ocean would not be quiet. The surface of molten rock is in constant motion, bubbling, roaring, and cracking as currents shift and gases escape. Imagine the hiss and pop of lava meeting seawater today, but magnify it to cover the whole planet. Explosive eruptions would punctuate the constant low roar as bubbles of gas burst from beneath the surface and hurled fountains of magma skyward. The noise would have been deafening, a thunderous symphony of fire and stone echoing across the newborn world. And what would it have felt like? The heat alone would have been unbearable, radiating outward in waves so intense that any solid object nearby would melt or vaporize. The air, if one could call it that, would be filled with choking gases, carbon dioxide, sulfur dioxide, methane and water vapor, dense and poisonous to any form of life we know. The pressure of steam and ash would create a suffocating heavy sky, dark yet glowing faintly rare with reflected firelight. The ground, if touched, would yield like a liquid, shifting and flowing beneath you, a reminder that Earth at this time was not a stable home, but a cauldron of creation. Despite how alien this sounds, scientists were not guessing blindly. Evidence for the magma ocean comes from both geology and physics. The Earth's layered structure, its iron core, silicate mantle, and rocky crust suggest that the entire planet was once molten, allowing heavier materials to sink and lighter ones to rise. Computer models of planetary formation also show that the energy from collisions, combined with radioactive heating and gravitational compression, would have been more than enough to keep the planet's surface liquid for millions of years. Even the Moon offers clues. The rocks brought back by astronauts show that the Moon too once had its own magma ocean, It cooled more quickly than Earth because of its smaller size, but the similarity suggests that this stage of planetary youth was not unique. Many rocky worlds, when newly formed, were likely seas of molten rock before they became the planets and moons we recognise today. Comparisons to modern volcanoes help give a sense of scale. When a volcano erupts today, the rivers of lava can flow for kilometres, shaping the land as they cool. But those flows are tiny compared to a planet-wide magma ocean. The lava lake at Kilauea's summit, as dramatic as it is, would be like a single drop in the fiery sea that once covered Earth. Even the largest known eruptions in human history, such as the flows that form the Deccan Traps in India, pale in comparison to the molten expanses of the young Earth. It was as though every volcano that has ever erupted was active at once, their flows merging into a single global sea. One of the most striking features of the magma ocean would have been the temporary formation of crust. As the surface radiated heat into space, thin skins of solid rock would sometimes form, darkening against the glowing magma. But these crusts were fragile, quickly broken apart by currents below or shattered by new impacts from space. Chunks of crust would sink back into the molten depths, recycling again and again. The Earth was trying to cool, but the process was constantly interrupted, leaving it trapped in a fiery balance between heat and escape. It is tempting to see the magma ocean as pure destruction, but it was also creation. Within its molten depths, elements mixed and sorted, forming the layered structure that still defines Earth today. The core's formation generated a magnetic field, which would eventually help shield the planet from harmful solar radiation. The outgassing from the molten mantle created the first atmosphere, laying the groundwork for the air we breathe. Even in its most violent and unstable state, the magma ocean was already shaping the conditions for the planet's future. If you could step back and look at this world from afar, you might be struck by its beauty as much as its violence. A glowing sphere in the darkness, wrapped in a halo of smoke and gas, pulsing with energy. It would have looked alive even before life had begun. The contrast between the cold emptiness of space and the fiery turbulence of Earth would have been breathtaking, a reminder of how dynamic and restless planets can be in their youth. Eventually, of course, the magma ocean would begin to cool, though the process took millions of years. But in this fiery stage, Earth was at its most dramatic, a world defined by molten chaos. The sight of it would have been unforgettable, a vision of creation on the grandest possible scale. And though no eyes were there to see it, the echoes of that fiery past remain, locked within the rocks beneath our feet and the restless rumblings of volcanoes that still break through the surface today. The magma ocean was not a gentle beginning. It was hot, loud, and utterly hostile to life as we know it. Yet within its molten heart lay the seeds of stability, the first steps toward the cooling, the oceans, and the landscapes that would one day define the Earth. It was a world that looked like chaos, but was, in truth, the earliest stage of order, shaping the planet into the place we now call home. More than 4 billion years ago, Earth was already a fiery, restless place, but its most dramatic moment was still to come. Among the countless collisions that shaped the young planet, one impact stands out as the most cataclysmic of all. Astronomers call it the Giant Impact, and from its chaos came one of Earth's most enduring companions, the Moon. The story begins with a wanderer. In the crowded early solar system, the region around Earth was full of large planetesimals, each one on its own unpredictable path around the Sun. One of these bodies, roughly the size of Mars, crossed paths with the growing Earth. Scientists have given this ancient world the name Theia. Its orbit was unstable, and gravity eventually drew it inward, until there was no avoiding a collision. What followed was not just another impact, but one of the most extraordinary events in planetary history. When Theia struck Earth, the energy released was beyond anything we can truly imagine. This was no mere asteroid strike. It was a head-on collision between two planets. The impact melted vast regions of both worlds, blasting molten rock and vaporized material high into space. Entire chunks of Earth's mantle were hurled into orbit, forming a glowing halo of debris around the planet. The surface of Earth itself was reshaped in an instant. Its molten ocean stirred like a cauldron. From this chaos, the moon began to take form. The debris thrown into orbit did not remain scattered for long. Gravity, ever the quiet architect, began pulling the fragments together. Within a surprisingly short span of time, astronomers think perhaps only months or years, these pieces coalesced into a single body. The early moon was born hot, glowing, and much closer to Earth than it is today. In those first moments, it would have loomed huge in the sky, a fiery orb above a fiery planet. Evidence for this story comes not just from imagination, but from the rocks themselves. Lunar samples brought back by astronauts during the Apollo missions show a striking similarity to rocks on Earth. Their isotopic fingerprints are nearly identical, suggesting that the moon formed not from a completely separate body, but from the very same material as the Earth's mantle. This fits beautifully with the giant impact hypothesis. The moon is, in a sense, a piece of Earth itself, sculpted into a separate world by a violent encounter. The moon's early appearance would have been extraordinary. Newly formed, it would have been covered in its own magma ocean, glowing like a lantern above the molten Earth. Over time, it cooled and solidified, leaving behind the craters and basins we can still see today. The moon we know now, with its quiet grey surface and stillness, is the calm descendant of that fiery birth. The arrival of the moon did more than give Earth a companion in the night sky. It profoundly changed the planet's future. One of its most important roles has been stabilizing Earth's rotation. Without the moon, Earth's axis might have wobbled chaotically, tilting one way and then another under the gravitational pull of the sun and other planets. Such instability would have meant wild shifts in climate, making it far harder for life to gain a foothold. The moon's steady gravitational pull acts as an anchor, keeping Earth's tilt within a relatively narrow range. Thanks to this, the planet has maintained a degree of stability over billions of years, allowing the long, slow story of life to unfold. The moon also gave Earth tides. The gravitational tug of the moon pulls on Earth's oceans, creating the rhythmic rise and fall of water across the globe. In the distant past, when the moon was much closer, tides were even stronger, shaping coastlines and stirring the chemistry of shallow seas. Many scientists believe these tides may have played a role in the early evolution of life, cycling nutrients and energy in ways that promoted complexity. Another gift of the moon is its influence on Earth's rotation. When it first formed, the moon orbited much nearer to Earth than it does today, and Earth spun far faster, completing a day in only a handful of hours. The gravitational interaction between the two has gradually slowed Earth's rotation, lengthening days to the 24-hour rhythm we now live by. At the same time, the moon has slowly drifted farther away. Even today, it continues to recede at a rate of a few centimeters each year. In the distant future, the Earth and moon will be locked in a kind of mutual embrace, always showing the same face to one another. It is fascinating to reflect on how much of our world is shaped by this ancient collision. The beauty of the full moon rising, the predictability of tides, the stability of seasons, all are consequences of that single fiery encounter more than 4 billion years ago. Had Theia never struck Earth, our planet might be unrecognizable, perhaps less stable, perhaps less hospitable, and perhaps lacking the familiar light that has guided countless human eyes and imaginations through the night. Even today, traces of the impact linger within Earth itself. Some geologists believe that remnants of Theia may still exist deep in Earth's mantle, vast regions of unusual material buried far below the surface. If so, then the moon is not the only reminder of the collision. Earth itself still carries within it the memory of that catastrophic meeting. From destruction came creation. The collision that nearly tore Earth apart instead gave rise to a companion that has shaped our planet ever since. The moon is more than just a silent satellite drifting above us. It is a fragment of Earth's own body, born in fire, forged in violence, and transformed into a stabilizing presence that has guided the planet's story for billions of years. When you look up at the moon tonight, you're not just seeing a grey and cratered rock. You're gazing at a relic of Earth's own fiery youth, a reminder that even the most violent beginnings can lead to enduring beauty. The gentle glow that soothed the night sky was once molten debris flung from a planet in chaos, and without it, Earth would be a very different place. The moon is both scar and gift, a child of fire that became a guardian of stability, and a constant reminder that creation often comes hand in hand with catastrophe. Above the glowing surface of the young Earth, the air was no refuge. The sky was as restless as the molten world below, thick with fumes and vapours that poured endlessly from the planet's fiery heart. Volcanic eruptions were constant, each one belching gases into the air, filling the atmosphere with carbon dioxide, methane, ammonia, sulphur compounds and clouds of ash. It was a sky that bore little resemblance to the calm blue we take for granted today. Instead, it hung heavy and suffocating, a haze of smoke and fire. The early atmosphere was not born gently. It came into existence through a process known as outgassing. As the magma ocean churned and volcanoes erupted, trapped volatiles within the molten rock escaped and billowed upward. Steam, carbon dioxide and sulphur dioxide were among the first to rise, and they stayed, gathering around the planet like a thick shroud. In these early days, the air was not something one could breathe, even if lungs had existed. It was toxic, heavy and dense, more like the emissions from 1,000 volcanoes erupting at once than the crisp atmosphere of modern Earth. This veil of gases meant the sky itself was not blue. Blue skies require a relatively clear atmosphere, where light from the sun scatters off nitrogen and oxygen molecules, but on the young Earth, sunlight had to pass through a soup of dust, vapour and thick greenhouse gases. The result would have been skies that glowed with rusty reds, hazy oranges and dim greys. At times the planet may have seemed cloaked in twilight even at midday, with only a weak glow from the sun penetrating the haze. The greenhouse gases filling this sky played an important role in the planet's story. Carbon dioxide and methane trapped heat, keeping the surface hot even as the Earth slowly radiated energy into space. Without them, the planet might have cooled far more quickly. Instead, they created a thermal blanket, holding in warmth and ensuring that fire dominated for millions of years longer. While deadly to any life we know, this toxic greenhouse atmosphere helped maintain the molten state of the young Earth. Sulphur gases added their own flair to the spectacle. Sulphur dioxide, once lofted into the air, can form aerosols, tiny reflective particles that scatter light. Today we see echoes of this in volcanic eruptions that tint sunsets with deep reds and purples. On early Earth, the effect would have been magnified many times over. Every horizon would have glowed with surreal hues, as if the entire planet lived under a permanent volcanic sunset. It would have been breathtakingly beautiful, and utterly hostile at the same time. Imagine standing at the edge of a molten plain gazing upward. The sun would appear dim, a muted disk behind veils of smoke. Around it, the sky would shift in shades of orange and crimson, blending into darker tones of purple and grey near the horizon. Ash and aerosols would scatter light into dramatic patterns, while streaks of lightning, triggered by the churning atmosphere, forked across the sky. This was a world where fire and smoke ruled the heavens just as much as the land. Such lightning storms were likely frequent. Volcanic plumes carry immense electrical charge, and with so much activity, the skies above the early Earth would have been alive with flashes of light. Each bolt would have cracked across the haze, illuminating the landscape in blinding bursts. The rumble of thunder would have echoed endlessly, blending with the constant roar of erupting volcanoes. The air itself was a stage for ceaseless drama. Although the sky was filled with smoke and fire, it was also a chemical laboratory. The gases swirling overhead were the raw materials for the planet's future. Carbon dioxide would eventually feed plants and form the backbone of the carbon cycle. Water vapour would condense into the rains that filled oceans. Even methane and ammonia may have played a role in the chemistry that seeded the first living systems. What looked like a toxic wasteland was, in truth, a planetary cauldron brewing the conditions that would one day support life. It is intriguing to compare this early Earth to its planetary neighbours. Venus, with its thick carbon dioxide atmosphere, offers a haunting glimpse of what Earth might have remained had conditions not shifted. Its skies are still filled with haze and sulphur clouds, its surface locked in an inferno. Mars, on the other hand, lost much of its early atmosphere, leaving behind a thin, cold sky. Earth's path lay somewhere between these fates, a balance that eventually gave rise to a breathable, life-supporting air. But in those earliest days, Earth's skies were closer to Venus than to anything we would now call inviting. The heavy blanket of gases also meant that stars would rarely have been visible from the surface. Unlike today, when the night sky reveals countless pinpricks of light, the early Earth would have been shrouded. Nights may have glowed faintly red, the haze reflecting the fire below. The moon, if visible at all through the haze, would have appeared as a ghostly lantern, blurred and distorted by the dense atmosphere. One of the most striking features of these skies would have been the sunsets. Today, the scattering of light gives us golden evenings and fiery twilights. But on early Earth, the haze of dust and gases would have stretched these colours across the entire sky. The whole dome above may have glowed with deep crimson, fading into purple shadows, the effect so intense it would make modern sunsets seem pale by comparison. Standing on that world, you would have witnessed skies that looked more like paintings than reality, vast, shifting murals of smoke and fire. Even though these skies were toxic and dangerous, they were vital to Earth's evolution. They trapped heat, shielded the surface from some of the sun's harshest rays, and kept volatile chemicals close enough to the surface to interact with oceans and rocks. They were in effect, the middle ground between the fiery Earth below and the cold vacuum above, a restless buffer where chemistry shaped the destiny of the planet. In time, these gases would be transformed. Water vapour would condense into rain, carbon dioxide would be drawn into rocks and later into living organisms, and oxygen would eventually rise to fill the sky. But long before any of that happened, Earth was a planet of smoke and fire. To look up was to see the atmosphere itself alive, glowing with colour, streaked with lightning, and filled with the breath of a world still learning to be a planet. The skies of early Earth remind us that beauty and danger often go hand in hand. They were deadly to breathe, oppressive to stand under, and yet they carried the seeds of everything to come. Beneath their crimson haze, the molten planet waited for the chance to cool, while above, the air churned and glowed, an ever-changing canvas painted by fire. It was a world where every horizon burned, every sunset stretched across the sky, and the air itself whispered of transformation. When you picture the Earth today, it is easy to imagine continents as immovable fixtures, vast slabs of land stretching across the globe, anchored in place as if they had always been there. But in the earliest days of the planet, there were no continents, no familiar landscapes, and no stable ground on which anything could rest. Earth was not a world of continents and oceans. It was a world of fire, its surface an ever-shifting sea of molten rock. At first glance, it might seem odd that continents did not appear right away. After all, the planet was full of rock and minerals, and gravity was already pulling things together. Shouldn't solid land have been inevitable? The problem was heat. The young Earth was drowning in it. Collisions during the planet's formation had released unimaginable energy, melting nearly everything. Radioactive elements within the mantle produced more heat as they decayed. Add to this the constant rain of asteroids and comets crashing onto the surface, and you had a recipe for a planet that could not keep a solid skin intact for long. Any attempt at forming a crust was short-lived. As molten rock spread across the globe, the surface radiated energy into space, creating thin, brittle layers of cooling rock. But those crusts were fragile. They cracked, sank, or were melted anew by the lava ocean below. It was a bit like trying to form ice on the surface of boiling soup. A film might appear, but it would quickly break apart and vanish back into the broth. On early Earth, land had no chance to stabilize. If you could hover above this molten world, you would see plates of dark, solidified rock drifting across fiery seas, only to fracture, sink, or be swallowed again. The surface would have resembled a colossal cauldron, with hardened fragments floating like croutons on an endless stew of magma. None of them lasted. Even the largest slabs were constantly recycled, pulled downward by the restless currents of the molten mantle. The difficulty of crust formation lay in the planet's internal structure. As Earth differentiated, heavy elements like iron and nickel sank into the core, while lighter silicates floated to the surface. This created a mantle that was constantly in motion, heated from below and cooled from above. Hot material surged upward, cooler material sank downward, and the surface was caught in the middle of this relentless convection. Imagine a pot of porridge bubbling on the stove. The surface rises, cracks, and falls, never still, always reshaping. That was the face of Earth in its earliest era. Modern volcanoes provide a small glimpse of this fiery instability. When a lava flow cools, it often develops a thin crust on top. If you have ever seen footage of lava creeping across the ground in Hawaii, you will notice that the surface darkens and hardens quickly, but the glowing magma beneath pushes through, cracking it again and again. On the young Earth, that same process occurred not just locally, but globally. Every attempt to form land was undone by the relentless heat below. Adding to the challenge was the constant bombardment from space. The early solar system was full of leftover debris, asteroids, comets, and planetesimals still wandering the sun's orbit. Earth was a frequent target, struck again and again. Each impact reheated the crust, shattering any fragile stability. Some collisions were large enough to vaporize entire regions of the surface, returning solid rock to liquid fire in moments. In this chaotic era, the ground itself could not be trusted to hold still. The absence of continents also meant that Earth's surface was a uniform world, lacking the features we now associate with planetary landscapes. There were no mountains, no valleys, no rivers. Instead, the surface was dominated by the rolling, molten tides of the magma ocean. The only topography came from the shifting flows of lava, the rise and fall of convection currents, and the scars of impacts. It was a landscape in constant flux, where nothing remained the same from one moment to the next. And yet, within this airy instability, the seeds of future continents were already present. Even as crust fragments melted and reformed, some minerals began to differentiate. Lighter rocks, such as those rich in silicon and aluminum, were more buoyant than the heavier iron-rich materials beneath them. Over immense spans of time, these lighter components would play a key role in the rise of true continents. But in the earlier stages, the heat was simply too great for them to gather and persist. The lack of stable continents also shaped the young Earth's climate and chemistry. With no land to erode, there were no soils, no rivers carrying minerals, no weathering of rocks to draw carbon dioxide out of the atmosphere. Instead, volcanic outgassing dominated the air, filling it with carbon dioxide, methane, and sulfur compounds. These gases trapped heat, feeding the cycle of fire that kept the crust unstable. The Earth was locked in a feedback loop, its fiery surface sustaining a smoky greenhouse sky, and that sky ensuring the surface remained molten. Comparisons to other worlds highlight just how unique Earth's journey was. Venus, too, may have once had a magma ocean, and today its surface is still dominated by volcanic plains. Its thick atmosphere of carbon dioxide likely prevented large-scale continental formation. Mars, on the other hand, cooled more quickly due to its smaller size. Though it never developed vast continents like Earth, it achieved a degree of stability far earlier. Earth's restless balance between fire and cooling delayed the appearance of continents, but ultimately allowed for a more complex geological story. If you were to describe the Earth at this stage, you might say it was a planet still deciding what it wanted to be. The ingredients for continents were there, but the heat of youth kept them suppressed. It was a world defined by impermanence, where land could not endure, and where the very concept of a continent was still millions of years away from reality. Despite its instability, this molten stage was not wasted time. The repeated melting and recycling of crust allowed materials to mix thoroughly. Elements were distributed across the mantle and crust in ways that would later prove essential for life. The recycling also allowed lighter minerals to accumulate slowly, forming the foundation of the first protocontinents once the planet finally cooled enough. In this sense, the lack of stability was itself a form of preparation, setting the stage for the land masses that would eventually rise. To imagine this world is to let go of the idea of permanence. There was no safe ground, no reliable landmark, no place that stayed the same from one moment to the next. Continents, in the sense we know them, did not exist. The Earth was still far too young, too hot, and too restless to offer such stability. Instead, it was a shifting sea of lava, its surface a restless tide of molten rock that refused to hold still. Yet within that fiery chaos lay the first hints of what would come, the fragments of crust that briefly floated, the lighter minerals beginning to separate, and the endless recycling of molten rock. All of these were steps on the long road toward a planet with land and oceans, mountains and valleys. For now, though, Earth was a world without continents, a place where fire ruled without interruption, and where the very idea of land was still a dream waiting to solidify. Across the young Earth's molten surface, there were no rivers of water carving valleys or winding their way toward distant seas. Instead, the first rivers were rivers of fire. They flowed not with cool, life-giving liquid, but with glowing rock, streaming downhill in brilliant currents that shimmered red, orange, and gold. These were the veins of a planet still in its infancy, coursing with heat and energy rather than water and life. Lava, in its essence, is rock that has been heated to such extremes that it behaves like a fluid. When it flows, it does so slowly, yet with a power that reshapes everything in its path. On modern Earth, volcanic eruptions provide small glimpses of this fiery behaviour, lava spilling from rifts in Iceland, or molten streams creeping across the fields of Hawaii. But the scale of the early Earth's rivers of fire was far greater. They were not local flows spilling from single volcanoes, but vast torrents moving across a global magma ocean. Imagine standing above such a scene suspended in the thick, hazy atmosphere. Below you, waves of lava stretched in every direction, a restless surface of liquid stone. Instead of valleys, you would see channels carved into the molten crust, where faster-moving currents cut through the slower cooling layers. The surface glowed with shifting colours, the brighter regions marking hotter, fresher flows, while darker crusts hinted at areas just beginning to solidify. From afar, the effect would have resembled the veins of a living creature, with fiery streams branching, merging, and spreading across the planet's skin. These molten currents were more than spectacles. They were sculptors of the planet. Just as rivers of water on modern Earth shape valleys, deltas, and floodplains, rivers of lava created ridges, channels, and vast plains of cooled stone. When lava spread and cooled, it formed new crust. When it broke apart, it recycled the surface. The entire landscape was in motion, shifting like an artist's canvas that could never remain finished. Every flow added new layers, erased old ones, and carried the story of Earth's youth forward. The behaviour of these fiery rivers depended on their temperature and chemistry. Hotter, thinner lavas moved quickly, streaming like glowing syrup across the surface. Cooler or thicker lavas crept slowly, their surfaces folding and wrinkling into strange textures. Some formed smooth, ropey patterns as they cooled, while others cracked into jagged formations that looked like broken glass. Today, geologists can still see these textures in lava fields around the world, echoes of the same processes that once dominated the entire globe. In places where currents collided, dramatic fountains would erupt. Pressure from beneath forced magma upward, spraying it into the air in glowing arcs that rained back down to the surface. These fountains added to the noise of the young planet, a constant crackling roar punctuated by bursts of molten spray. Each explosion reshaped the terrain, scattering new material that would soon melt back into the flow. The rivers of fire were not cisterns, not steady streams. They pulsed, shifted and branched, sometimes surging forward in great waves, other times slowing to a sluggish crawl. Their paths were dictated by the restless currents within the mantle below. Convection in the mantle acted like an unseen engine, pushing magma upward in some places and dragging it downward in others. The surface was simply the reflection of this deeper turbulence, its fiery rivers tracing the hidden movements of the planet's interior. The effect on the atmosphere was profound. Every flow released gases into the sky, carbon dioxide, sulfur dioxide, water vapor and methane, feeding the thick, hazy shroud that cloaked the earth. Lightning storms raged above as volcanic plumes charged the air. Ash clouds mingled with the smoke, scattering sunlight into eerie hues. From the ground, the horizon would glow not with the blues and greens of today's world, but with reds and oranges, like an eternal sunset cast across the entire planet. For all its violence, there was something mesmerizing about this world of fire. Watching the molten currents must have been like staring into a gigantic, slow-motion ocean of light. Waves of rock rolled against each other, merging and parting, glowing brighter where they were hottest and fading darker as they cooled. From above, the planet would have looked alive, pulsing with glowing veins of magma that shifted across its surface like the breath of a great fiery organism. These rivers of fire were also vital for shaping the Earth's future. By carrying heat from the interior to the surface, they allowed the planet to cool, however slowly. Each flow released energy into space, radiating it away in the form of light and heat. Without these fiery channels, Earth might have stayed molten for much longer. They were the planet's first cooling system, a way of venting the energy trapped during its violent formation. As lava cooled, it left behind layers of basalt and other volcanic rocks. These layers built up over time, creating the first hints of a solid crust. Though fragile and constantly recycled, they mark the beginning of a surface that could eventually stabilize. The rivers of fire, in their endless motion, were laying down the groundwork for continents and oceans yet to come. If you compare them to modern rivers of water, the parallels are striking. Just as water carves valleys and transports sediments, lava carved channels and spread minerals, just as rivers of water eventually meet the sea, lava rivers often merged into vast molten plains, pooling before cooling into wide plateaus. The key difference, of course, was that these rivers were far hotter and far more destructive, capable of melting anything in their path. Where water nourishes, lava consumed. Yet both were forces of change, carving landscapes and shaping the destiny of the planet. It is worth remembering that the Earth we live on still carries traces of this fiery past. Modern volcanic eruptions are not new phenomena, but echoes of a time when the entire world was a volcanic field. Every time lava flows across a landscape today, we are watching a miniature version of what once defined the entire globe. The rivers of fire may no longer dominate Earth, but they have not disappeared. They continue to flow in certain corners of the world, reminders that the heat of Earth's infancy still lingers deep within. To imagine Earth as a world of molten currents is to see it at its most raw and elemental. No continents, no oceans, no forests or deserts, only rivers of fire weaving across a glowing surface, painting the planet in shifting shades of red and gold. It was a harsh world, but also one of extraordinary beauty, a living canvas of molten light. And though it was dangerous, toxic and unstable, it was the necessary beginning, the fiery stage upon which the later chapters of Earth's story would one day unfold. If you could somehow find yourself standing on the surface of the young Earth, eyes closed, trying to take in the sound of the world around you, you would not be greeted by silence. There were no birds in the sky, no rivers trickling through valleys, and no leaves rustling in the wind. But there was sound, overwhelming, endless, and thunderous. The early Earth was a planet alive with noise, and the music it played was one of fire. The most constant sound would have been the crackle and roar of molten rock. Picture the hiss of lava meeting air in Hawaii, or the low rumble of an erupting volcano. Then magnify that until it filled the whole horizon. The magma ocean that covered Earth's surface shifted and churned, its fiery currents colliding with each other, breaking through thin crusts, and pouring in bright cascades that hissed and spat as gases escaped. Every bubble of carbon dioxide or sulfur dioxide rising from the molten depths burst with a sharp core crack, adding to the endless percussion of the planet. Volcanoes were not occasional features but the very skin of the Earth. Everywhere you turned, plumes of fire and ash erupted skyward. Each explosion carried with it a deep, booming roar, the kind of sound that rattles through your chest when you hear thunder up close. These eruptions were on scales that dwarf anything humans have ever witnessed. Ash clouds would have filled the sky with a muffled, growling hiss, while glowing fountains of lava roared like jet engines, throwing molten rock hundreds of meters into the air before it fell back to join the sea of fire. And then there were the impacts. The early solar system was still full of wandering asteroids and comets, each one a potential intruder. When they struck Earth, the sound would have been beyond anything comprehensible. Imagine the crack of a meteorite landing on solid ground today, then scale it up until the collision melted whole regions of the planet. These impacts released so much energy that their thunder would have rolled across the globe, reverberating through the molten crust like the beat of a cosmic drum. Each impact was not just a crash, but a detonation, a deafening shockwave that tore through the dense atmosphere, shaking the world. The atmosphere itself added its own voice to this symphony. Thick with gases and ash, it was a restless, turbulent sky. Lightning storms were frequent, sparked by the violent churning of volcanic plumes. Each flash was followed by a booming peal of thunder, magnified by the density of the air. Thunder would not have been a distant rumble, but a constant crashing drumbeat echoing above the molten plains. The dense gases also carried sound differently. Low, rumbling noises would have stretched and lingered, wrapping around the listener like waves of pressure. If you tuned your senses to the subtler notes of this fiery orchestra, you would hear the delicate crackling of cooling rock. Thin crusts that briefly formed on the magma ocean snapped and fractured under the strain, their brittle edges breaking with sharp popping sounds. Each time molten currents surged beneath the surface, the crust shattered, sending a cascade of crackles rippling outward. It would have been a little like the sound of ice breaking on a frozen lake, except hotter, sharper, and far more ominous. In the background of all this was the constant hiss of gases escaping from the mantle. Steam, carbon dioxide, sulfur, and methane vented endlessly into the sky. Think of the sound of 1,000 geysers erupting at once, or the hiss of a massive pressure valve slowly releasing. That was the planet's breath. A ceaseless exhalation that filled the air with both sound and poison. Weather, as we think of it, did not yet exist. There were no rains, no rivers, and no winds sweeping across continents. Yet there was still something like weather. Storms of ash and gas. Winds whipped through volcanic plumes, scattering particles across the sky with a whispering, rushing noise. Ashfall would have pattered against molten surfaces like rain on a metal roof, each grain sizzling as it touched down. Instead of gentle breezes or ocean waves, the atmosphere carried the shriek of turbulent winds fighting their way through dense clouds of smoke and fire. Even silence was rare. On modern Earth, we can find quiet in deserts, forests, or deep caves. But the early Earth had no such places of calm. The molten planet was never still. Sound was as constant as heat and light, a reminder of the energy still trapped inside this young world. The closest thing to silence would have been the low, ever-present hum of the magma ocean itself, a bass note that never stopped, as though the entire planet were vibrating with its own heartbeat. To imagine this world fully, Think of the sounds of modern volcanoes combined into a single symphony. The hiss of lava cooling against air, the crackle of rock breaking under strain, the roar of fountains of fire bursting from the ground, the thunder of lightning storms overhead, the ground-shaking boom of an asteroid strike, and above it all, the steady hiss of gases venting skyward. This was the soundtrack of Earth's infancy. For humans, such an environment would have been uninhabitable, deafening, and terrifying. Yet in another sense, it was mesmerizing. The sounds were chaotic, but they were also rhythms of creation. Each eruption, each crack, each rumble of thunder was part of the process of shaping the world. To listen to the young Earth was to hear the very act of a planet becoming itself. And while those sounds have long since faded, they are not gone entirely. Modern eruptions still echo the roar of that fiery past, the hiss of lava flowing into the sea, the crackle of cooling rock, the boom of volcanic thunder, all are whispers of what once filled the entire planet. The Earth no longer screams with fire the way it once did, but its voice can still be heard if you know where to listen. The early Earth was not a silent, empty sphere. It was a planet of sound, every note born of fire and impact, every rhythm forged in chaos. To stand there would have been to hear creation itself, a restless, thunderous, crackling world where the music of molten stone never ceased. For a brief moment in its youth, Earth might have seemed like it was beginning to calm. The magma ocean was slowly trying to form crust. Thin plates of rock floated across molten seas, and gases built a dense and smoky atmosphere. But peace never lasted for long. Above the planet, space itself was full of danger. Millions of rocky fragments, asteroids, and icy comets left over from the formation of the solar system. And for Earth, these fragments did not remain distant. They fell. Astronomers call this violent period the Late Heavy Bombardment, a time when the solar system rained stone and ice upon the young worlds. Imagine meteors streaking through the sky, not once a month, not once a year, but constantly, an endless hail of fire from space. Some were the size of boulders, others the size of mountains. Each one struck with unimaginable force, releasing energy that rivaled the most powerful explosions the planet has ever known. The early solar system was not yet neat and orderly. Planets had only recently carved out their orbits, and many smaller bodies were still wandering in chaotic paths. The gravitational pull of the giant planets, especially Jupiter and Saturn, sent countless asteroids and comets hurtling inward. Earth, with its growing mass, became a prime target. To an observer, the sky would have looked alive with streaks of light, fiery trails burning across the haze as objects tore into the atmosphere. When these visitors struck, the results were catastrophic. The kinetic energy of an asteroid impact is staggering. Even a rock only a few kilometers wide carries enough momentum to release more energy than millions of nuclear bombs combined. When it hit, the crust shattered, molten rock was thrown skyward, and shockwaves rippled around the globe. For a planet already struggling to cool, each impact reheated the surface, undoing whatever fragile stability had begun to take hold. The crust was cracked, melted, and swallowed back into the fiery mantle below. The sheer frequency of impacts meant Earth's surface was in a state of perpetual upheaval. Craters overlapped craters, their rims blasted apart by newer strikes before they could ever cool. Some collisions were so massive they vaporized entire regions of rock, turning solid land back into glowing plasma. The air filled with ejecta, molten fragments of stone flung high above the atmosphere before raining back down in fiery showers. To anyone watching, the planet would have seemed caught in a cosmic firestorm, glowing from both above and below. The moon preserves the scars of this era. Unlike Earth, it has little atmosphere, and no plate tectonics to erase its history. Its surface remains pocked with craters, a permanent record of the storm of impacts that raged across the solar system. Every crater on the moon is a reminder that Earth, too, was struck by countless objects, its surface reshaped again and again. The difference is that Earth's restlessness has since smoothed over the scars, burying them beneath oceans, continents, and shifting crust. But in the Moon's face, we see a reflection of our own violent past. Comets added their own role to this bombardment. Unlike rocky asteroids, comets are rich in ice, and when they collided with Earth, they delivered water as well as destruction. Some scientists believe that a significant fraction of Earth's water may have arrived this way, carried within icy projectiles from the outer solar system. Each collision was a paradox, catastrophic in the moment, yet essential for creating the oceans that would one day cradle life. It was as if the heavens themselves were throwing both fire and water at the Earth, shaping its destiny through contradiction. The bombardment also contributed essential chemistry. Many asteroids carried organic molecules, complex carbon compounds forged in the cold depths of space. When these rained down onto the fiery Earth, they seeded the surface with ingredients that would later play a role in life's emergence. To think of it another way, the same impacts that scorched the crust and filled the skies with fire were also delivering the seeds of biology. Destruction and creation arrived hand in hand, wrapped in the same cosmic package. The atmosphere during this era would have been a strange place to witness. Every impact lit the sky with blinding fireballs, brighter than the sun as objects tore through the air. Shockwaves rippled outward, flattening anything in their path. Dust and ash from impacts darkened the skies for weeks or months at a time, blotting out the sun and leaving the surface in eerie twilight. Then, as the debris settled, the greenhouse gases released from molten rock and vaporized materials trapped heat, creating intense warmth again. The climate swung violently between searing heat and choking gloom, a cycle dictated not by seasons, but by the rhythm of falling stones. In terms of sound, the bombardment would have been deafening. Each impact sent shockwaves that cracked the air and echoed through the ground. The roar of erupting magma combined with the thunder of atmospheric entry, followed by the bone-shaking boom of collision. For long stretches, Earth would have been nothing but a cacophony of explosions and crashes, the air trembling with the constant violence of the skies. Despite its violence, the bombardment was temporary. Over time, the number of wandering bodies in the solar system dwindled. Jupiter and Saturn cleared out much of the debris, either by swallowing it or flinging it into the outer reaches of space. Earth continued to absorb its share, but gradually the rain of fire eased. The planet could finally begin to cool more steadily, crusts of rock surviving longer without being shattered anew. Yet for millions of years the Earth had endured a storm so intense it reshaped everything about its surface and its destiny. Looking back, the late heavy bombardment was both a trial and a gift. It delayed Earth's cooling, ensuring the planet remained a world of fire for longer than it otherwise might have. But it also delivered water, organic molecules, and a rich mix of elements that would later become part of soils, seas, and living cells. The firestorm from space was both destroyer and benefactor, carving scars even as it planted the seeds of life. To picture Earth in this era is to imagine a world under siege. From the heavens came streaks of light that ended in fireballs, each one a blow powerful enough to remake the surface. The crust melted and reformed, the skies darkened and glowed, and the planet itself seemed caught in an endless battle with the cosmos. Yet within that battle lay the beginnings of oceans, the chemistry of biology, and the chance for stability to emerge. The heavy bombardment was not a punishment, but a stage of growth. Every crater, every molten scar, every shower of fiery debris was part of the process of becoming a planet capable of life. And while it may have looked like destruction from afar, in truth it was creation in disguise, the universe's way of shaping Earth into the cradle it would one day become. Earth's youth, when its surface glowed with magma seas and its skies burned with haze, may seem impossibly distant. Yet even today, the universe offers glimpses of worlds that live as Earth once did. To study them is to look backward in time, as though peering through a cosmic mirror. Among the most striking examples are our neighbouring planet Venus and Jupiter's fiery moon Io. Each is a world where lava still dominates, reminders that the universe is not done with fire. Venus is sometimes called Earth's twin, and in terms of size and composition, the nickname fits. Both planets are roughly the same diameter, both are made of similar materials, and both formed in the same region of the solar system, but the resemblance ends when you step onto the surface. Venus is cloaked in an atmosphere of carbon dioxide nearly 100 times thicker than Earth's, with clouds of sulfuric acid that shroud the planet in perpetual gloom. The surface temperature is hot enough to melt lead, a suffocating furnace where rocks themselves glow with heat. This inferno is sustained in part by volcanism. Radar mapping from spacecraft has revealed vast plains of basalt, evidence of lava flows that once swept across the planet. Volcanoes, some hundreds of kilometers wide, rise from the surface, their flanks shaped by rivers of molten rock that hardened long ago. More recent studies suggest that Venus may not just have an ancient volcanic history, but an active one. In recent years, scientists have spotted changes in volcanic vents, indicating eruptions may still be occurring today. If true, Venus is not simply a world that once echoed Earth's fiery past, but one that still carries it forward. The landscape of Venus is frozen in fire. Without plate tectonics to recycle its crust the way Earth does, lava has instead resurfaced much of the planet in massive floods. Entire regions appear smoothed over, as if someone had poured molten rock across thousands of kilometers at once. On Earth, lava is usually confined to narrow channels or localized eruptions. On Venus, it has drowned continents. The result is a world that feels eerily young and old at the same time, its surface reshaped in geologic bursts, yet locked in a perpetual state of stifling heat. In this way, Venus may resemble what Earth could have become had its path diverged slightly. A little closer to the Sun, a little more greenhouse trapping, and perhaps our planet too might have been a furnace wrapped in haze. Venus is a cautionary reflection, a vision of Earth if it had failed to cool and balance its climate. To gaze at Venus is to see the Earth that might have been, a reminder of the thin margin between habitability and hostility. While Venus offers a large-scale echo of Earth's fiery youth, Io provides a more immediate spectacle. This small moon of Jupiter is the most volcanically active body in the solar system. Unlike Earth, whose volcanoes are scattered and intermittent, Io's surface is in a near-constant state of eruption. Dozens of active volcanoes dot the moon, some sending fountains of lava hundreds of kilometers high, while rivers of molten rock spread across plains that can be seen from space. The source of Io's fire is not internal heat from radioactive decay or lingering energy from formation, as on Earth, but the relentless pull of Jupiter's gravity. As Io orbits, it is tugged and flexed by Jupiter and its neighbouring moons, a process called tidal heating. This constant squeezing generates immense friction inside Io, melting its interior and fueling the eruptions that remake its surface again and again. To put it simply, Io is kneaded like dough by Jupiter's gravity, and the result is a world that never rests. From afar, Io's landscape is a bizarre mixture of beauty and danger. Patches of yellow, red and white mark sulfur compounds scattered across its surface, giving it a strangely painted appearance. Black scars of cooled lava flows snake-cross plains, while enormous volcanic mountains rise above fields of molten stone. Unlike Earth, Io has no oceans, no weather to soften its features, and no tectonic plates to recycle its crust. Instead, it is a raw volcanic world, one that may resemble Earth at its most active, magnified, and frozen in time. For scientists, Io is a living laboratory. It demonstrates what happens when volcanic activity dominates a world entirely. Its constant eruptions provide a window into processes that shaped Earth in its infancy, helping us understand how molten surfaces behave, how atmospheres are influenced by volcanic gases, and how heat escapes from restless interiors. Watching Io is like glimpsing Earth's past playing out in real time, only with Jupiter looming in the background as an enormous overseer. Taken together, Venus and Io are reminders that fiery worlds are not confined to the past. They exist now, scattered throughout the solar system, each one carrying lessons about Earth's earliest state. Venus shows us the fate of a planet that never escaped its greenhouse haze, locked into a furnace where lava once and perhaps still flows. Io shows us what happens when volcanism becomes all-consuming, a surface that never settles, always reshaped by fire. And beyond our solar system, astronomers have begun to find exoplanets that may themselves be lava worlds. Some orbit so close to their stars that their surfaces must be oceans of molten rock, glowing with heat under skies filled with vaporized minerals. To imagine them is to imagine Earth during its infancy, fiery orbs circling suns, unstable yet full of potential. The universe is dotted with these reminders, as if to reassure us that Earth's fiery youth was not unique, but part of a wider cosmic pattern. There is something strangely comforting in this perspective. Earth's past may seem distant, but it is reflected in the present of other worlds. To look at Venus or Io is to glimpse a chapter of our own history. They remind us that fire is not just destructive but creative, that worlds must pass through violence to achieve stability. In the glow of Io's eruptions and the haze of Venus's atmosphere, we see shadows of the Earth that once was, and in those shadows we find a deep appreciation for the fragile balance we live within today. The cosmos, it seems, is full of fire. Planets and moons are born in it, shaped by it, and sometimes consumed by it. Earth has largely moved past its fiery childhood, but the memory lingers in volcanoes, in basalt plains, and in the slow rumble of tectonic plates. Venus and Io are the siblings that never left that stage, each one locked in his own fiery rhythm. To reflect on them is to remember that our world, too, was once ablaze, a glowing ember in the dark of space waiting to cool, to change, and eventually to give rise to life. The Earth did not stay a molten world forever. Even in the midst of fire, the planet was slowly losing its heat to the great cold of space. Radiation carried energy outward, a steady glow that seeped from the magma ocean into the void. Though the surface blazed with temperatures over 1,000 degrees, space was near absolute zero, an infinite reservoir that drew away Earth's warmth day after day, year after year. Gradually the furnace began to cool. This cooling was not uniform or simple. The planet's interior remained hot for a very long time, and still does today, but the surface was the first to begin changing. As heat radiated outward, thin skins of solid rock appeared on the molten seas. These early crusts were fragile and short-lived, breaking apart under the stress of convection currents or shattering when new impacts tore across the surface. Yet each time the crust reformed, it grew a little thicker, a little more stable. The fiery skin of Earth was turning piece by piece into stone. The process can be compared to soup cooling in a pot. At first, bubbles burst and the surface refuses to stay calm, but leave it long enough and a thin film begins to form, floating on top of the liquid. On Earth, that film was the earliest crust, basaltic rock hardened from molten lava. It was not yet the granite-rich continents of today, but it was a beginning. The formation of this crust changed everything. Where molten rock had flowed like slow rivers, now it began to freeze into black volcanic plains. Waves of lava still surged from below, cracking and consuming these rocky plates. But for the first time, there was something to stand upon, if anyone had been there to try. Though the crust was unstable, constantly fractured and recycled, it marked the transition from a purely molten world to one that carried both fire and stone. Cooling was aided by the gradual decline of bombardments. As fewer asteroids and comets rained from the sky, the surface had longer stretches of time to recover between impacts. Each calm interval allowed new layers of rock to solidify. Though collisions still came, reshaping and melting what had already formed, the intervals of stability slowly lengthened, and the crust thickened with every cycle. The crust did not form evenly across the planet. Some regions cooled more quickly, creating larger patches of solid ground, while others remained fluid seas of lava. These patches drifted and cracked, colliding with one another like rafts on a molten ocean. When they met, they sometimes merged, building larger stretches of rock. In other cases, one slab would sink beneath another, pulled downwards into the still molten mantle. These early motions foreshadowed the tectonic activity that would one day define Earth's geology. Above, the atmosphere bore witness to the cooling below. As the surface lost heat, volcanic outgassing continued, filling the skies with steam, carbon dioxide and sulfur. But the cooling crust allowed some of these gases to condense. Steam in particular began to form clouds, heavy with water that would eventually fall as rain. At this stage, the rains were not yet persistent or strong enough to fill oceans, but the first droplets fell onto rock instead of magma, hissing into steam as they touched the hot surface. It was the beginning of water meeting stone, the first step toward rivers and seas. The crust also provided new textures to the planet's surface. Instead of endless glowing magma, Earth began to display dark basaltic plains, cracked with fissures that glowed where lava still surged through. From orbit, the planet would have looked less like a blazing ember and more like a patchwork of blackened rock veined with fire. The light of Earth's glow dimmed slowly as more of the surface hardened and less molten rock was exposed to space, yet the cooling was never absolute. Heat from the interior continued to push upward, breaking through the crust in towering volcanic eruptions. Entire fields of solid rock were drowned beneath new lava flows. Even now, billions of years later, Earth still erupts in this way, though today only in scattered places. In its youth, the entire surface was a volcanic plain, constantly remade. Cooling was not a straight line towards stability, but a tug-of-war between heat escaping and heat rising anew from the mantle. Despite the turmoil, this balance tipped slowly toward calm. Each layer of hardened rock trapped heat within, but also insulated the mantle beneath, forcing it to find new pathways upward. Over millions of years, this cycle of eruption, cooling and hardening transformed Earth from a fiery sphere into a planet with a surface that could endure. The presence of a crust altered more than the planet's geology. It also provided a stage on which future chemistry could play out. Solid rock exposed to steam and gases created new reactions, producing minerals that could not have formed in pure lava. These minerals, in turn, shaped the composition of the atmosphere and oceans that were still to come. The crust was not just a physical barrier, it was a chemical frontier, where the story of Earth's transformation continued in subtler ways. In contemplating this shift, there is something poetic about fire becoming stone. A planet once defined entirely by molten chaos was learning to cool, to settle, and to hold still. The crust was fragile, yes, but it was a sign that stability was possible. Earth was no longer only a furnace but a world in transition, carrying the memory of its fiery past within layers of black volcanic rock. This cooling process has never truly ended. Even today, Earth sheds heat into space, though at a much slower rate. The solid crust we walk upon is thick and stable compared to those early days, but beneath it, the mantle still churns, and at the centre, the core still glows with primordial heat from the planet's birth. Every eruption we witness now is a reminder of that ancient balance, fire pushing upward while stone holds steady above. To imagine Earth during this stage is to picture a world dimming slowly, its vagary glow fading as the first continents of rock tried to form. The air was still heavy with smoke, the sky still streaked with lightning, but the surface was no longer an endless sea of fire. There were patches of land, unstable though they were, and the planet's face was beginning to look less like a star and more like a world. The cooling of the furnace was not the end of Earth's fiery story, but it was the beginning of a new chapter. For the first time there was ground, however fragile, and a balance was forming between the planet's molten heart and the cold of space. It was this balance, delicate and imperfect, that set the stage for oceans to gather, skies to clear, and eventually for life to find a home on stone rather than fire. For millions of years, Earth's skies had been filled with steam. Volcanoes breathed it out in endless streams, geysers of vapour rising from the molten mantle, mixing with carbon dioxide, sulphur and methane to form a dense and choking shroud. The air was hot, the pressure immense, and water could not fall as rain. It lingered as vapour, swirling in heavy clouds that cloaked the fiery planet below. But slowly, as Earth radiated its heat into space, something remarkable began to happen. The atmosphere, though still thick and hostile, cooled just enough to let that steam condense. The first raindrops began to form. It is difficult to exaggerate how extraordinary this moment must have been. Imagine a planet that had only ever known fire suddenly tasting water for the first time. Clouds swelled with moisture, heavy and unstable, or until they could no longer hold it. Droplets gathered, growing large enough to fall through the dense air. They plunged downward, pulled by gravity, rushing toward a surface that had never before felt their touch. For the first time rain fell on Earth. The sight would have been surreal. From the heavens came sheets of water tumbling in torrents through an atmosphere already heavy with smoke and haze. But the ground was not solid stone cooled by millennia of calm. It was hot, black volcanic crust split by rivers of lava, glowing cracks that pulsed with molten fire beneath the surface. When the raindrops struck, they sizzled instantly, vaporizing into plumes of steam. Each drop was erased in a hiss, a fleeting contact between two elemental forces, fire and water. The sound of that first rain would not have been the gentle patter familiar to us today. Instead, it was more like a violent chorus of hissing and crackling. Imagine pouring water onto an iron skillet heated until it glows red. Now magnify that sound until it covers an entire planet. The crust shuddered with the sudden contrast, and plumes of steam burst upward, thickening the atmosphere with even more clouds. The cycle repeated itself endlessly, water falling, vaporizing and returning to the sky. Yet not all the rain was lost. As the surface cooled, certain regions grew stable enough for droplets to survive more than an instant. Tiny pools began to collect in cracks and depressions, though they often boiled away as soon as they formed. Over time, as the crust thickened and the heat lessened, these pools endured longer. They steamed and bubbled, but they persisted. In the most sheltered places, the planet was beginning to hold water. This was not yet the formation of oceans, but it was the beginning of the long transition. Each rainfall carried energy away from the atmosphere, cooling it further. Each droplet that struck the ground absorbed heat, releasing steam that rose skyward and spread the cycle wider. It was a planet-scale balancing act, fire and water locked in a struggle, each reshaping the other. From a chemical perspective, these first rains were more than just water falling from the sky. They carried dissolved gases from the atmosphere, carbon dioxide, sulphur dioxide, and other compounds. When they struck the hot rock, they reacted, leaching minerals and altering the chemistry of the crust. These early reactions laid the foundation for the cycles that would later regulate Earth's climate. Carbon dioxide, for instance, began to be drawn down into minerals through weathering, though the process was slow and often undone by the new eruptions. The simple act of rainfalling was, in truth, part of the great planetary laboratory that was preparing Earth for life. The imagery of this era is striking. Blackened volcanic plains steaming under relentless rainfall, rivers of lava glowing as they met cascading sheets of water, geysers of vapour rising in response. Lightning storms cracked above, illuminating the spectacle in brilliant flashes. It was not a quiet rain, but a furious one, as if the skies and the surface were at war. Yet in that conflict, a fragile truce was forming, one that would eventually allow the planet to transform from a world of fire into a world of seas. Modern analogues help us imagine this clash. When lava flows into the ocean in Hawaii, enormous clouds of steam billow skyward, punctuated by explosions as water and a molten rock violently interact. On early Earth, this scene was not limited to coastlines. It was everywhere. Every raindrop carried with it the potential for a miniature explosion. Every flow of lava met with hissing and boiling as water fell from above. The entire surface was engaged in this elemental dialogue. In time, the balance began to tip. The crust thickened, eruptions grew less frequent, and the atmosphere cooled enough for rains to persist. Storms gathered and fell in torrents, pouring water faster than it could evaporate. Steam still rose in clouds, but more and more of the water remained behind, pooling in low-lying regions, carving channels, and gathering into vast basins. These were the seeds of the oceans, born from countless raindrops that had first been rejected by fire, but finally found a place to rest. The significance of that first rainfall cannot be overstated. It was the beginning of Earth's transformation into a planet where water would dominate the surface. Today, over 70% of the globe is covered in oceans, and nearly all life depends on water. Yet all of it began with that initial condensation, with vapor cooling enough to fall, with the hiss of droplets striking molten stone. There is also something deeply poetic in the image of fire and water meeting for the first time. These are elements often portrayed as opposites. One destroys, the other nourishes. Yet on the young Earth, their interaction was not merely conflict, but creation. Fire provided the energy to release gases into the air, water condensated from those gases, and together they began to shape a planet capable of supporting life. Their struggle was not the end of either, but the forging of balance. To imagine standing on that early Earth, you would see skies dark with storm clouds, lightning forking across the heavens, and sheets of rain pouring down in endless cascades. Beneath your feet, the ground would glow with lava flows, steaming and crackling under the deluge. The air would be thick, hot, and heavy with vapor. Every breath would taste of minerals and ash. Yet in that storm lay the seeds of calm, the first steps toward oceans, rivers, and the cycle of water that would one day sustain forests, animals, and people. The first raindrops may have seemed small, but they carried with them the weight of transformation. They were more than water falling from the sky. They were the planet cooling, the atmosphere changing, the stage being set for oceans to spread and for life to begin its slow, improbable journey. Those hissing droplets marked the beginning of Earth's shift from a world ruled by fire to a world balanced between fire and water, a world on the path to becoming the blue planet we know today. The rains that first fell on Earth began as a hiss, droplets turning to steam as they struck molten stone. But over time, as the crust thickened and the furnace cooled, more and more of that water remained behind. What had once been vapor hanging heavy in the skies began to pool upon the ground. This was the moment when Earth's transformation became undeniable, the moment oceans arrived. The water that gathered on Earth did not come from a single source. Much of it was born deep within the planet, locked away in minerals during its violent formation. As volcanoes erupted across the surface, they released steam into the air. Each eruption belched out clouds of gas that rose into the thick atmosphere, joining the cycle of condensation and rainfall. Slowly, drop by drop, the atmosphere gave back what the mantle had released, and that water began to stay. Yet volcanic breath was not the only source. From the outer reaches of the solar system came icy messengers, comets and water-rich asteroids flung inward by the gravitational influence of the giant planets. These frozen travellers, when they collided with Earth, shattered into fragments and released their icy cargo. Each impact was violent, often catastrophic, yet it also delivered precious water to a world that desperately needed it. Between volcanic outgassing and these celestial deliveries, the young planet was being stocked with enough water to cover its surface. As the rains fell harder and longer, low-lying regions of the crust began to fill. The first true bodies of water formed in vast depressions, steaming lakes that shimmered in the haze. They boiled and bubbled at first, for the ground was still hot and unstable, but gradually they endured. Streams of the runoff carried more water into these basins, and the lakes grew. In time, as rainfall became torrential and unrelenting, these pools merged into something larger. Lakes became seas, seas became oceans, until the face of Earth was transformed from fiery plains into a water world. The appearance of the first oceans must have been extraordinary. Imagine standing on one of the early patches of solid crust and looking out over a horizon where the land simply ended in blue. The water stretched into the distance, reflecting the dim light of the sun through a haze of clouds. Steam rose in tendrils from the surface, curling into the air as droplets evaporated, but much of the water remained. For the first time, Earth was wrapped not only in sky but in seas. The sound of these early oceans would have been unfamiliar to us. Without established winds, without shorelines shaped by time, the waves would have been irregular, surging unpredictably against the still cooling crust. Steam hissed where water touched volcanic fissures, punctuated by the deep rumble of distant eruptions. It was not yet the calm rhythm of tides lapping a beach, but something rougher, more primal, as the planet adjusted to its new balance between fire and water. The chemistry of these newborn seas was unlike the oceans we know today. Dissolved gases from the atmosphere mixed into the water, creating a brew rich in carbon dioxide, sulfur, and other compounds. The seas were acidic and heavy with minerals leached from the volcanic crust. Yet within this harsh mixture lay the ingredients that would one day foster life. The oceans were not only a physical transformation, but also a chemical stage where molecules mingled and reacted in ways impossible on a dry, fiery world. The sheer volume of water was staggering. Today, Earth's oceans hold over 1 billion trillion litres of water, enough to cover the planet's surface to an average depth of nearly 4 kilometres. In its infancy, as water first pooled, the basins may not yet have been that deep, but they grew quickly. The relentless rains, combined with continued delivery from icy impacts, filled the depressions until the surface was dominated by blue. What had once been a planet of fire was now a planet of seas. The skies, too, began to change. Where once the atmosphere had been choked with steam and smoke, it now cycled water more efficiently. Clouds thickened, condensed and poured their rain, but the balance shifted as more water remained on the surface. The greenhouse haze persisted, but gradually the skies cleared enough for sunlight to reflect off the oceans. For the first time the young Earth gleamed, not as a glowing ember of magma, but as a shimmering, water-wrapped sphere. To imagine this transformation from a cosmic perspective is awe-inspiring. From space, Earth no longer glowed red and gold with fire but shone blue, veiled by white clouds. It was a new kind of beauty, different from the molten spectacle of its infancy. The oceans became mirrors, catching light and scattering it into the darkness of the solar system. To any distant observer, the planet had been remade. The arrival of oceans also brought stability. Water is an extraordinary regulator of heat. It absorbs energy, distributes it, and releases it slowly. With oceans in place, Earth could begin moderating its temperature more effectively. The violent extremes of heat and cooling softened into gentler rhythms. Though volcanic eruptions still reshaped coastlines and asteroid impacts occasionally boiled regions of sea, the overall balance tilted towards calm. The oceans had become a buffer, protecting the crust from the full intensity of the sun and the interior alike, and with water came the first cycles that would define Earth for billions of years. Rain fell, collected, evaporated, and rose again into clouds. Minerals dissolved into the seas, settled into sediments, and formed new rocks. Gases exchanged between air and water, shaping the atmosphere. The water cycle, fragile at first, became the heartbeat of the planet, a continuous loop that connected sky, sea, and stone. There is something soothing about picturing these first oceans despite their strangeness. The surfaces may have been harsh, the chemistry unwelcoming, but the sight of vast blue waters must have brought a sense of calm to a planet long ruled by fire. Waves rolled against rocky shores, Steam curled lazily into the sky, and clouds drifted above, heavy with the promise of more rain. For the first time, Earth had seas, and with them came the potential for life. Today, when we gaze out at the ocean, we see stability, continuity, and life itself. But every swell, every tide is connected to that first gathering of water billions of years ago. The oceans we know are ancient beyond imagination, their origins rooted in fire, steam, and ice. They began as raindrops hissing against lava, as icy comets shattering against the crust, as gases bursting from the mantle into the skies. All of that energy, all of that chaos, eventually settled into calm blue waters. The arrival of oceans was the single most transformative moment in Earth's history after its very formation. Fire had built the planet, but water gave it its character. Fire forged the stone, but water shaped the surface, balanced the climate, and prepared the way for life. It was the moment Earth became not just a rocky planet, but a world capable of nurturing complexity. To close your eyes and imagine those first oceans is to drift into a soothing vision, a planet remade, fire softened by water, chaos tempered by rhythm. Waves lapped against volcanic shores, clouds rolled gently above, and the air, though still harsh, carried the promise of change. The seas had come, and with them the Earth was no longer only a furnace, it had become a cradle. When Earth's oceans first spread across its surface, they must have seemed boundless. Vast basins of water covered much of the planet, leaving only scattered fragments of land struggling to stay above the waves. But eventually, through fire and upheaval, the first islands appeared. They were not lush or green, not havens of birds or trees, but bare and black, their surfaces newly hardened from volcanic fire. These islands were the earliest signs that Earth was beginning to shape geography as we would one day recognize it. The emergence of islands was driven by the same restless forces that had always defined the planet, volcanism and tectonics. Deep within the mantle, heat continued to rise. Magma surged upward through cracks and weaknesses in the crust, breaking through in eruptions that built up new land above sea level. The process was relentless. Each eruption spilled lava onto the surface, cooling and hardening to form rock. Layer by layer, these flows accumulated until they rose above the waters, forming islands. At first, these islands were small and fragile. Waves battered their edges, breaking down the youngest rocks and carrying fragments back into the sea. New eruptions sometimes destroyed as much as they created, splitting islands apart or drowning them beneath fresh lava. But despite their instability, they were something new, the first protrusions of Earth's surface that could be called land. Modern volcanic islands offer a glimpse into what this must have looked like. Consider the Hawaiian archipelago, where lava fountains and flows gradually build islands in the middle of the Pacific. Each eruption adds to the land, pushing it higher above the sea. On the early Earth, this process happened on a far greater scale, scattered across oceans that were still forming. The islands would have been stark, steaming, and lifeless, but they represented stability in a world that had long been nothing but fire and water. Over time, volcanic activity concentrated in certain regions, creating clusters of islands. These groups of volcanic peaks were the first hints of proto-continents. Unlike today's continents, with their complex layers of granite, sandstone, and sediment, these early land masses were simple piles of basalt, hardened lava stacked over millennia. Yet they were larger and more enduring than the solitary volcanic peaks that had come before. For the first time, Earth carried patches of land big enough to shape weather patterns, to influence ocean currents, and to provide a stage for chemical processes that might someday nurture life. The rise of protocontinents was also tied to the planet's internal differentiation. Lighter silica-rich rocks, formed from the repeated melting and recycling of crust, were more buoyant than the denser basalt below. These lighter rocks floated higher on the mantle, creating land that could resist sinking back into the molten depths. The result was the gradual appearance of more substantial land masses, capable of surviving the constant assault of waves and eruptions. The sight of these first proto-continents must have been dramatic. Imagine sailing over the young seas, if such a thing were possible, and seeing jagged peaks rising from the water, their slopes still glowing in places with fresh lava. Steam would have billowed from cracks where rain met magma, and the air would have carried the sharp scent of sulfur and minerals. These were landscapes still in the process of being born, places where the boundary between fire and water was constantly tested. Though barren and harsh, the islands were important for Earth's developing systems. They provided surfaces for rainfall to collect and run off, carving the first streams and rivulets into solid rock. Minerals were leached into the seas, enriching the chemical mix that filled the oceans. In time, weathering of these rocks would help regulate the atmosphere, drawing down carbon dioxide and contributing to the long-term balance of the climate. Land was more than scenery. It was a key player in the planet's transformation. The oceans too were affected by these rising land masses. Waves broke against rocky shores, creating new dynamics in the water cycle. Currents flowed differently, guided by the contours of the protocontinents. Where waves pounded cliffs, fragments of rock were ground into sand and gravel, settling into the seabed as the earliest sediments. These processes, though subtle at first, were the beginnings of the geological cycles that still shape Earth today. It is tempting to picture these islands as lonely dots in a vast expanse of ocean. And in many ways they were, but to the young Earth, they represented enormous progress. Only a short time before, the surface had been nothing but fire. Now it was fire and water, and now, at last, stone rising above water. The contrast was striking, a sign that the planet was moving toward greater complexity. These early islands and protocontinents would not have lasted forever. Many were swallowed back into the mantle through subduction, or buried under new flows of lava. Others were broken apart by impacts from asteroids that still occasionally rained down from space. The surface of Earth remained restless, never allowing land to grow entirely stable. But each cycle of destruction and renewal built up more material, more buoyant rock, and more enduring land masses. Stability, though still far off, was slowly gathering strength. From a cosmic perspective, the appearance of land was significant. A water world without continents behaves very differently from one with them. Continents anchor climates, redirect winds and currents, and provide niches for ecosystems. In their absence, a planet is uniform, its surface smooth and featureless. By raising islands above the seas, Earth introduced variety into its face. The first unevenness in what had been a world of monotony. Even in their lifeless state, these protocontinents were striking features of the planet. Seen from space, they would have appeared as dark scars upon the shimmering blue of the seas. Clouds would gather around their peaks, drawn by convection as air rose over the land. Lightning storms would cluster there, their crackling fury illuminating the rough outlines of the islands below. In this way, the land was already interacting with the atmosphere, subtly influencing the patterns of weather and water. The poetic contrast is hard to miss. A planet born in fire had now called forth water, and from that water rose fire once again, solidified into stone. Lava, cooled and hardened, stood against the seas, resisting the endless wash of rain and waves. Fire had created water, and water in turn was now reshaping fire into land. Earth had begun to find its balance, not yet calm but no longer defined by chaos alone. When we look at continents today, vast stretches of granite mountains and fertile plains, it can be difficult to imagine them as the descendants of those humble beginnings. Yet every landmass we walk in can trace its ancestry back to the first islands that broke the surface, to the jagged volcanic peaks steaming under ancient skies. They were the planet's first attempt at permanence, the earliest signs that Earth was capable of building more than molten seas and endless rain. In those islands rising from the fire sea, the first hints of stable geography appeared. They were not yet continents as we know them, nor were they enduring in the way we think of land today, but they were a promise. They were the beginning of Earth's face taking shape, of geography written in stone. From the interplay of fire and water, Earth had drawn forth its first land, a fragile but vital foundation for all the wonders still to come. From its very beginning, Earth has been a restless planet. Beneath the crust lies a mantle that never quite sits still, a churning sea of molten rock that pushes upward, breaks through, and spills out onto the surface. Volcanism is the outward expression of that restlessness, the way the planet exhales the heat and gases trapped within its depths. It is no exaggeration to call volcanism Earth's lifeblood, for without it the planet would not have the atmosphere, the oceans, or even the continents that define it today. When Earth was young, this breathing was constant and fierce. Gases locked within the mantle surged upward with each eruption, bursting into the skies in colossal plumes. Carbon dioxide, sulfur dioxide, water vapor, methane, and nitrogen poured into the air, changing the composition of the atmosphere with every outburst. These gases shaped the world as profoundly as the lava that built mountains. The atmosphere itself is, in large part, the exhalation of a planet. To put it simply, Earth was learning how to breathe fire. It might seem odd to think of volcanoes as part of a breathing process, but in many ways that is exactly what they are. The mantle acts like the lungs of the planet, drawing in energy from radioactive decay and the lingering heat of formation, then releasing it through eruptions. Each plume of smoke and ash is a planetary exhale, a sign that the planet is alive inside. If Earth had been silent and still, locked under an unbroken crust, it would have remained a suffocating sphere, unable to build an atmosphere or regulate its own temperature. Volcanism is messy, destructive and noisy, but it is also the way Earth finds balance. The gases released through volcanism were not uniform. Water vapor was one of the most abundant, and it played a central role in forming Earth's oceans. Every eruption vented steam into the skies, where it condensed and fell as rain. Without these volcanic exhalations, the seas would never have filled. Alongside the water vapor came carbon dioxide, which built the greenhouse effect that kept Earth from freezing during its early years when the sun was dimmer than it is today. Nitrogen, too, was carried upward in volcanic breaths, eventually becoming the dominant component of the modern atmosphere. Not all volcanic gases were so helpful. Sulfur dioxide, for instance, created acrid clouds and acidic rains, and methane added to the greenhouse warming in unpredictable ways. But even these less friendly gases were vital to shaping the planet's chemistry. They formed the raw material for reactions in the oceans and atmosphere, reactions that eventually gave rise to the conditions in which life could emerge. Every unpleasant belch of Earth's fiery lungs carried the seeds of future possibility. The style of volcanism during those early times was different from what we know today. Modern eruptions, though powerful, are scattered and localized. On the young Earth, volcanic activity was nearly everywhere. Entire plains were formed by enormous lava flows, some stretching for hundreds of kilometers. Picture a world where eruptions the size of modern-day Iceland's Laki or India's Deccan Traps were not rare catastrophes but common events. The skies would have been filled with ash on a regular basis, sunsets painted in red and gold not by weather but by volcanic haze. These eruptions were more than surface displays. They were signs of the planet's interior working out its balance. Heat trapped inside needed to escape, and volcanic vents were the pressure valves. Without them, the planet might have overheated and remained locked in molten chaos. By venting both heat and gases, volcanoes allowed the crust to harden, the seas to remain stable, and the atmosphere to grow. They were dangerous, yes, but also essential. Imagine walking along the surface of that world if survival were possible. Around you, cones of basaltic rock rose like chimneys, glowing at their tips with fountains of lava. Rivers of molten stone flowed down their sides, steaming as they met rainwater or seas. Above, plumes of ash and gas billowed upward, spreading across the sky. The ground trembled with each eruption, and the air was thick with the hiss of escaping steam. It would have seemed chaotic and terrifying, yet this was simply the Earth breathing, exhaling the products of its own interior. Even today, the legacy of this fiery breathing remains. Volcanoes still dot the planet, from the fire belts around the Pacific to the mid-ocean ridges that stretch like scars across the seafloor. They are fewer and more isolated than in the planet's youth, but they remind us that Earth is still alive inside. Every plume of smoke from Stromboli, every eruption from Kilauea, every hiss of steam from Icelandic vents is part of the same process that once filled the skies with fire. Humans often think of volcanoes only in terms of destruction. They bury cities in ash, trigger tsunamis and disrupt climates, but they are also creators. Volcanic rock builds islands, fertile soils grow on their slopes, and minerals released in eruptions become part of life's building blocks. Even the air we breathe is in part the gift of countless eruptions that vented nitrogen and oxygen precursors into the sky. When you take a breath, you're inhaling a mix that was shaped by the long exhalations of the Earth itself. There is a gentle humour in thinking of Earth as a planet that once coughed, sputtered, and finally learned to breathe steadily. In its youth, its volcanic lungs were overactive, filling the skies with smoke and flame. Over time, as the planet cooled and stabilized, its breathing slowed, but it never stopped. Earth may not breathe fire as often now, but every once in a while it reminds us that it still can. The metaphor of breath also captures something deeper about volcanism, its role in keeping the planet in motion. Breathing is rhythm, an exchange of inside and outside, a sign of life. Earth's eruptions too are rhythmic. They release heat and gases, reshape the crust, and then pause before beginning again. On the grandest scale, they form cycles of activity that span millions of years, bursts of fire followed by quieter periods of calm. These cycles have guided Earth through climate shifts, mass extinctions, and the slow evolution of continents. To reflect on this is to see volcanism not just as a destructive force, but as the pulse of a living planet. Without it, Earth would be lifeless rock, inert and silent. With it, Earth became dynamic, breathing out the air that would one day sustain forests, animals, and people. Volcanism is messy, unpredictable, and sometimes frightening, but it is also the sound of Earth alive, exhaling its history with every plume of smoke. When you watch a volcano erupt today, you are witnessing more than a spectacle. You are watching the ancient breath of the planet, the same breath that once built an atmosphere, filled the oceans, and set the stage for life. Earth may not have lungs, but it does have a voice, and that voice speaks in fire. The first oceans did not begin as clear, blue waters stretching peacefully across the globe. They were steaming, mineral-rich cauldrons, restless and turbulent under skies heavy with volcanic clouds. Into these early seas poured the breath of the earth, gases from endless eruptions hissing through fissures in the crust, bubbling upward in plumes of steam. It was here, in the strange chemistry of fire meeting water, that the raw recipe for life was first mixed. Every volcanic eruption carried with it more than just heat and lava. Carbon dioxide, methane, ammonia, hydrogen sulfide, nitrogen, and water vapour rose in vast clouds and dissolved into the oceans below. These compounds mingled with minerals leached from newly cooled rock, creating a broth unlike anything found today. The seas of early Earth were not gentle, placid waters. They were reactive laboratories, fizzing with energy, rich in ingredients waiting for the right spark. Scientists call this stage prebiotic chemistry, the chemistry that came before biology. It is the period when simple molecules combined into more complex ones, laying the foundation for living systems. In those bubbling oceans, carbon joined with hydrogen, nitrogen, and oxygen in countless combinations, producing amino acids, nucleotides, and other essential building blocks. These molecules are the alphabet of life, and though they are tiny, their formation was the turning point between a barren planet and one that would eventually teem with organisms. The energy that powered this chemistry came in many forms. Lightning storms raged constantly above the seas, for volcanic plumes filled the skies with charged particles. Each bolt of lightning split molecules apart, allowing atoms to recombine into new structures. Ultraviolet light from the young sun, unfiltered by an ozone layer that did not yet exist, bathed the oceans in radiant energy, driving further reactions. And beneath the seas, hydrothermal vents gushed superheated water, rich in minerals and metals, providing both heat and chemical gradients that fueled even more complex interactions. It is remarkable to think of how much of this early chemistry came from fire. Volcanism not only built the crust and atmosphere, but also supplied the gases that filled the oceans with potential. Sulfur compounds from eruptions may have formed the basis of primitive metabolic pathways. Methane and hydrogen provided reducing conditions that made complex chemistry more likely. Even the iron released from volcanic rocks played a role, catalyzing reactions that built larger molecules from smaller ones. In a very real sense, Earth's fiery lungs were not only exhaling destruction, they were breathing the seeds of biology. The earlier seas must have looked strange to modern eyes. Instead of clear waters, they would have been cloudy with minerals, tinted by dissolved iron, sulfur, and other compounds. Some regions may have been deep red from iron oxides, others milky from silicates, others still yellowish from sulfur. Steam rose constantly where hot lava met water, creating foggy horizons. Bubbles fizzed at the surface, carrying gases from the mantle below. To wade into such a sea would not have been refreshing. It would have been like stepping into a bubbling laboratory where chemistry never ceased. One of the most intriguing possibilities is that life's first ingredients assembled in small sheltered environments along the shores of volcanic islands or near hydrothermal vents. Pools warmed by geothermal heat may have concentrated molecules enough for them to interact. Waves splashing against volcanic cliffs could have created thin films of liquid where reactions occurred more readily. In these microenvironments, chemistry was not random but guided by conditions that favoured complexity. Over immense spans of time, chance encounters between molecules became patterns, and patterns became the beginnings of order. The famous Miller-Urey experiment of the 20th century offered a glimpse into this process. By recreating a simplified version of Earth's early atmosphere and sparking it with the electricity, scientists found that amino acids, the building blocks of proteins, could form spontaneously. While the actual conditions of early Earth were more complex than the experiment suggested, the principle remains: with volcanic gases, water and energy, the chemistry of life can arise naturally. What took place in laboratories in the modern age had already been happening on a global scale billions of years ago. It is tempting to picture these early chemical soups as chaotic, and in many ways they were, but within the chaos lay pathways of possibility. Certain molecules are more stable than others, more likely to persist and accumulate. These survivors became the foundation for further complexity. Chains of carbon atoms formed, linking together into organic structures. Rings of molecules assembled, providing the scaffolding for nucleotides and eventually the first hints of genetic information. Though life itself had not yet begun, the alphabet of biology was being written letter by letter in the simmering seas. The role of fire in this story cannot be overstated. Without volcanism, the oceans would have been little more than distilled water, lifeless and inert. It was the gases vented from Earth's interior that enriched the seas with chemistry. Fire turned stone into minerals, minerals into solutions, and solutions into the stage where biology could appear. Earth was not only cooling, it was cooking, stirring a recipe whose outcome would change the planet forever. And what an extraordinary recipe it was. Water, gases, minerals, heat, and energy, all combining in countless ways, most of them fleeting, but enough of them enduring to build complexity. The seas became not just passive pools, but active cauldrons, their surfaces steaming, their depths alive with reactions. If the planet itself was a kitchen, then volcanoes were both the stove and the spice rack, providing the heat and the flavour that made the mix interesting. To imagine this chemistry unfolding is to see Earth at its most creative. The skies flashed with lightning, the oceans bubbled with gases, and the crust hissed with vents. Every environment offered a new possibility. Shallow pools, deep trenches, volcanic shores. Each was an experiment running simultaneously, a different trial in the grand laboratory of the planet. Most of these experiments led nowhere, molecules breaking apart as quickly as they formed. But some pathways persisted, refining themselves until, eventually, they crossed the line between chemistry and biology. Though life had not yet appeared, the groundwork had been laid. The fiery breath of volcanoes had filled the seas with carbon, nitrogen, and sulfur. The cooling rains had provided water in abundance. Lightning and sunlight had supplied energy. All the necessary pieces were in place, waiting for the improbable leap that would turn chemistry into living cells. It is humbling to consider how central fire was to this process. We often think of volcanoes as destructive, yet without them there would have been no air to breathe, no oceans to drink, and no chemistry to give rise to life. The same eruptions that blacken the skies also enrich the seas. The same fiery plumes that belch poison also delivered possibility. Fire, far from being an enemy of life, was one of its first allies. In the cauldron of early Earth, chemistry was destiny. Volcanic gases mixed with oceans, minerals dissolved and recombined, and energy sparked new arrangements. From these humble beginnings came the first whispers of biology. Fire had built the planet, water had softened it, and together they stirred the pot of creation. The seas were no longer only seas, they were laboratories, simmering with the ingredients of life. And though the recipe would take millions of years to finish, the first steps had already been taken in the bubbling, steaming, fire-fed cauldrons of a young and restless Earth. For countless ages after its fiery birth, Earth's skies were cloaked in haze. Thick with volcanic gases, ash and steam, they glowed red and orange, streaked with the smoke of eruptions and darkened by the dust of impacts. The sun, when it appeared at all, was a blurred disk behind curtains of cloud. The heavens were not yet blue, not yet calm, but slowly, almost imperceptibly, the atmosphere began to change. And with that change came a sight both new and familiar, the first clear, blue sky. The transformation began as Earth continued to cool. Volcanic eruptions still shook the land, but they grew less constant, less overwhelming. The endless storms of ash that once filled the air began to ease, leaving longer stretches of clearer sky between eruptions. The water vapour that had once hung in choking density now condensed into rain, pouring down in sheets and helping to wash dust and ash from the air. With every downpour, the atmosphere grew a little lighter, a little cleaner. As the oceans expanded, they acted as sinks for many of the gases that had thickened the air. Carbon dioxide dissolved into the waters, where it combined with minerals to form carbonates. Sulfur and other reactive compounds also found their way into chemical reactions, their concentrations in the sky slowly decreasing. With fewer of these pollutants scattering and blocking the light, the atmosphere became more transparent. The heavy veil that had hidden the heavens for so long began to lift. The chemistry of the air itself was changing too. Nitrogen, released from volcanoes and less reactive than the many other gases, gradually became the dominant component of the atmosphere. Though it is colourless and invisible, nitrogen provided the stability the skies needed. It allowed sunlight to pass through relatively unimpeded, and as oxygen slowly began to appear, first in trace amounts from photochemical reactions and much later in greater quantities from primitive life, the atmosphere became even more conducive to clarity. The result of all these changes was not immediate. It unfolded over millions of years, an atmospheric evolution measured in the slow accumulation of cleaner skies. One day, though no one was there to witness it, the haze must have cleared enough for sunlight to scatter properly. Instead of dim, ruddy light filtering through smog, the heavens above shone with a new brilliance. For the first time, Earth's sky appeared blue. The physics behind that colour is simple yet profound. Shorter wavelengths of sunlight, such as blue, scatter more easily off gas molecules than longer wavelengths like red. When the air was clogged with thick aerosols and dust scattering favoured reds and oranges. But once the haze thinned and molecules like nitrogen dominated, The shorter blue wavelengths spread across the sky. The world below was bathed in a cooler, calmer light, and the planet finally looked something like the one we know today. Imagine the moment from the perspective of the surface. For ages, the skies had been oppressive, heavy with smoke, their colours harsh and their light dim. Now, for the first time, there was openness, a dome of soft, endless blue arched overhead, interrupted only by drifting white clouds. The sun no longer flickered faintly through haze, but shone with clarity, its rays glinting off the oceans below. It was not just a change in appearance, but in mood. The world had grown calmer, gentler, more welcoming. That first blue sky marked a turning point. It was a signal that Earth had moved beyond its most chaotic youth, that the planet was finding balance. Fire and smoke still erupted from volcanoes, but they no longer dominated every horizon. Asteroid impacts still came, but less frequently, and their scars were less lasting. The rains that once boiled instantly now lingered, filling seas and lakes instead of vanishing into steam. The planet was transitioning from constant upheaval to something steadier. The emotional weight of this change is difficult to ignore. A blue sky is so ordinary to us now that we take it for granted. But on a young Earth, that blue sky was a profound novelty. It was the first sign that the planet's violence was softening, that the chaos of fire was giving way to rhythms of air and water. In that calm expanse of blue was the promise of stability, a promise that life could one day depend upon, even before oxygen levels rose enough to create the modern breathable atmosphere. The sight of a blue sky would have made Earth look more familiar than at any previous time. From space, the planet gleamed, with oceans and clouds beneath that azure dome. From the surface, the world no longer seemed trapped under a permanent storm, but open to the heavens. Earth was beginning to look less like a strange alien furnace and more like the home it would become. The arrival of the first blue sky also changed the way energy moved through the planet's systems. Sunlight now reached the surface more directly, warming land and water in predictable cycles. The contrast between day and night grew sharper. Clouds, once lost in the haze, now formed against a backdrop of clear air, their shapes drifting gracefully across the sky. Wind stirred more freely, guided by temperature differences across land and sea. Weather, in the sense we know it, was beginning to emerge. The symbolism of this shift is powerful. Earth had spent its youth hidden behind veils of fire and smoke, its face obscured, its skies smothered. The first blue sky was a revelation, the moment the planet had unveiled itself, as a world not only of fire and stone but also of air and light. It was a preview of the beauty that would one day define it, when forests and animals and people would all look up and see the same endless blue stretched above them. Though no eyes were there to witness it, the first blue sky was one of the most transformative sights in Earth's history. It signalled not only a change in chemistry, but a change in character. The world was still wild, still young, still restless with volcanism and storms, but it had taken a crucial step toward becoming recognisable. It had moved from a furnace to a home, from a haze-filled cauldron to a planet with skies open to the light. To reflect on that moment is to recognise the patience of nature. Billions of years of chaos, fire and upheaval were required before the skies could clear. Yet eventually they did, and when they did, Earth revealed a beauty that still defines it. The blue of the sky is, in a sense, the colour of calm, the signature of a planet that endured fire and storm long enough to become a cradle for life. The first blue sky was not just a change in atmosphere, it was a milestone in Earth's story. The moment when the world began to look like itself, the moment when chaos softened into calm and the heavens opened into a colour that would one day feel like home. Deep in the darkness of Earth's early oceans where sunlight could not reach, the planet's fire continued to shape the story of life. Along fractures in the crust, water seeped downward and met the molten heat of the mantle. There, it was superheated, charged with minerals, and driven upward again in plumes that erupted back into the sea. These were hydrothermal vents, the chimneys of a restless earth, where fire and water combined in one of the most extraordinary laboratories imaginable. Around these vents, the oceans shimmered with contrasts. The surrounding waters were cold and dark, but the vent plumes surged upward at temperatures of hundreds of degrees, rich with metals, sulfides and gases. Where they met the seawater, minerals precipitated out, building tall chimneys of black and white rock. These vents looked alien, otherworldly, yet within them stirred the conditions that would one day awaken biology. They were more than cracks in the seafloor. They were breathing places where chemistry came alive. The idea that life may have begun here is both scientifically compelling and poetically fitting. Hydrothermal vents provided everything the earliest chemistry required: heat, chemical gradients, and a steady flow of raw materials. The porous rocks of the vent structures offered tiny compartments, natural reaction chambers where molecules could be concentrated instead of drifting apart into the vastness of the ocean. In these sheltered spaces, simple compounds like carbon dioxide and hydrogen sulfide could react, forming organic molecules. Over time, complexity grew. Chains of carbon formed lipids, which assembled into primitive membranes. Amino acids linked into peptides. The building blocks of biology began to emerge. The key was energy. Life is, at its heart, the harnessing of energy to create order. In the vents, steep chemical gradients provided this energy in abundance. Hot, mineral-rich fluids gushed upward into cold, oxygen-poor seas, creating zones where reactions naturally occurred. Some of the earliest metabolic pathways may have been born from this contrast, simple cycles of energy capture that later evolved into the complex machinery of cells. Even today, many microbes living near hydrothermal vents use the same kinds of chemical reactions that could have powered life's first steps. To imagine this world is to picture a seafloor alive with strange beauty. Black smokers, tall chimneys of minerals, poured out plumes that billowed like underwater smoke. White smokers released lighter shimmering fluids, their towers gleaming with carbonate deposits. Around them the water sparkled with minerals, a shimmering haze of chemistry in motion. There was no sunlight here, no forests or skies, but there was energy, and in that energy there was potential. Fire and water, once enemies in Earth's youth, had become partners. The fire of the mantle heated the water, driving it upward with minerals in tow. The water, in turn, carried that chemistry into spaces where it could cool, concentrate and react. Together they created the balance necessary for life to begin. The seas above provided stability, while the vents below supplied energy. It was as if Earth itself was experimenting, trying combinations until the right recipe appeared. Modern discoveries lend weight to this vision. In the late 20th century, scientists exploring the seafloor discovered entire ecosystems thriving around hydrothermal vents. These communities of tube worms, clams, crabs and microbes live without sunlight, relying entirely on chemosynthesis, the use of chemical reactions, not photosynthesis, to create food. At the base of these ecosystems are bacteria and archaea that use sulfur and hydrogen as fuel, echoing the processes that may have sustained life from the very beginning. To find rich communities flourishing in such a place was a revelation. It proved that life does not require sunlight or oxygen to thrive. All it needs is energy, chemistry, and time. In the context of early Earth, this discovery is profound. It suggests that life could have started not in shallow sunlit pools as once thought, but in the deep oceans, where fire and water met in quiet partnership. Here, molecules could assemble without being broken apart by ultraviolet light. Here, the energy of chemical gradients was steady and constant, not dependent on storms or lightning strikes. The vents offered both shelter and opportunity, and in their warmth, the first cells may have stirred. To picture those first cells is to imagine something almost invisible yet unimaginably significant. Tiny bubbles or lipid membranes enclosed fragile strands of RNA or simple peptides. They absorbed energy from their environment, reproduced imperfectly, and competed for survival. They were not alive in the way we think of life today, but they carried the spark of it, the ability to change, to persist, to evolve. From these humble beginnings, the entire story of biology would unfold. What is striking about this moment is the quietness of it. The rest of the Earth was still a restless volcanic world, its skies heavy, its continents unstable. But in the hidden darkness of the oceans, something gentle was happening. Chemistry was becoming biology. Order was arising from chaos, and the line between non-living and living was being crossed. It was not a dramatic leap, but a gradual whisper, a slow accumulation of tiny successes that together formed the spark of life. The poetry of fire and water as twin cradles cannot be ignored. Fire gave the heat, the energy, the gases, and the minerals. Water provided the medium, the stability, and the space for chemistry to play out. Alone, neither could have created life. Together, they made a planet capable of nurturing it. It is a reminder that opposites often need each other, that creation is born not from one element, but from the meeting of two. Scientists continue to debate the exact details of how life began. Some favour shallow pools struck by lightning, others prefer the depths of hydrothermal vents. But in either case, the elements are the same: energy, chemistry, and time. Fire and water, once at odds, came together to set the stage. The vents are perhaps the most elegant version of this partnership, a constant dance of hot and cold, mineral and sea, chaos and order. Reflecting on this beginning, there is a calm reassurance in knowing that life came from such ordinary ingredients. There was no magic formula, no outside intervention, only the natural interactions of elements and energy. The same laws of physics and chemistry that shape stars and planets also shaped the first cells. The universe, in its patience, allowed a planet to cool, to breathe, and to mix fire with water until something new appeared. The spark of life was not a single flash, but a slow glow kindled in the cauldrons of the deep. It was nurtured by vents that exhaled the breath of the earth, carried by waters that spread across the globe, and strengthened by the cycles of fire and rain. From that delicate beginning, life would spread to fill the seas, the land, and eventually the skies. In the quiet of the deep oceans, the earth took its first living breath. The chimneys of fire exhaled gases, the waters received them, and in the mingling something remarkable happened. The spark of life was born, not in sunlight but in shadows, not in peace but in turbulence, not in stillness, but in the eternal rhythm of fire and water working together. And from that spark, everything we know, everything we are, would one day follow. The Earth's earliest years were a time of fire, but that faint fire did not vanish without leaving a trace. Its memory was written into stone. Ancient rocks, some billions of years old, are time capsules carrying whispers of a world we can no longer see. They are fragments of a youth lost to us in all but geology, and by reading them carefully, scientists have pieced together the story of Earth's molten beginnings. Not all of these rocks have survived. Most of Earth's earliest crust was recycled, melted back into the mantle, or shattered by tectonic shifts. The surface of the planet is restless, always remaking itself, and few stones endure across billions of years. Yet a handful of relics remain, found in places like Canada, Greenland, South Africa, and Western Australia. These are not merely rocks, but pages in the oldest chapters of Earth's diary, written in minerals instead of ink. Among the most precious are the zircon crystals of Western Australia. These tiny, nearly indestructible gems are over 4 billion years old, older than almost any other material on Earth's surface. Though small, they preserve within them isotopic clues that reveal the conditions under which they formed. Some zircon suggest that liquid water existed on Earth surprisingly early, perhaps only a few 100 million years after its formation. Others bear chemical signatures of crust that had already cooled and stabilized, even in the midst of the planet's fiery youth. These crystals are like sparks frozen in time, fragments of the planet's first experiments in becoming solid. The rocks of the Canadian Shield tell another part of the story. Their ancient formations, more than 3.5 billion years old, show patterns of volcanic activity, sediment deposition, and metamorphism. These are not just random layers of stone, but evidence of Earth's restlessness, of magma rising and cooling, of water carving channels, of heat reshaping minerals deep below. In these patterns, geologists see echoes of the fiery furnace that once defined the planet. Every rock carries memory in its minerals. Basalt, born of lava, whispers of eruptions that spilled across early plains. Granite, formed slowly from molten material cooling deep below, remembers the patience of heat contained. Sedimentary layers, though younger, capture the rains that fell on volcanic islands, the rivers that carried eroded ash into seas, the slow settling of particles over time. Even metamorphic rocks, transformed by heat and pressure, are like palimpsests, rewritten yet still bearing traces of their fiery origins. The isotopes within these rocks tell perhaps the most intimate stories. Ratios of oxygen, carbon, and other elements reveal the temperatures at which minerals crystallized, the chemistry of the waters that once flowed over them, the gases that filled the air above. Through these silent markers, geologists reconstruct a world that would otherwise be lost. A shift in isotope ratios might tell of a sudden cooling after an eruption, or of water circulating through hot crust. Each number is a ghost of conditions long gone, proof that the planet's fire left fingerprints everywhere it touched. There is poetry in the way rocks preserve memory. They do not speak in words but in textures, in grains and chemical compositions. A line of basalt frozen mid-flow tells of a river of fire that once coursed across the surface. A ripple pattern in sandstone records the lapping of waves against an ancient volcanic shore. A seam of quartz marks a crack where hot fluids once surged upward. The language of geology is subtle, but it is eloquent. It tells us that the fire of Earth's youth has not disappeared. It is simply hidden, carried forward as memory in stone. Even mountains, though much younger than Earth itself, bear the imprint of that fiery beginning. Their granite cores formed from molten rock that cooled slowly over eons. Their uplift and erosion are powered by tectonics, which in turn are driven by the heat still rising from Earth's interior. Every cliff face, every canyon, every pebble on the ground is connected to that ancient furnace. The rocks we walk upon each day are not just scenery, but the condensed story of fire becoming form. Volcanoes themselves provide the most direct reminder. When lava erupts today, it creates rocks nearly identical to those of Earth's earliest days. Basaltic flows spread across the land, cooling into black stone streaked with bubbles of gas. To pick up a piece of basalt from a modern eruption is to hold something that echoes the very material that once covered the planet. The continuity is striking. The processes that shaped Earth 4 billion years ago still shape it now, the fire that built the first crust still burning within. It is humbling to consider how little of that earliest crust remains. The Earth is a master of recycling, dragging plates into the mantle, erasing scars, remaking itself again and again. The fact that any rocks older than 4 billion years survive at all is astonishing. Each one is a rare survivor, like a letter that escaped the flames of a burning library. To study them is to hear faint echoes of a world otherwise gone. Yet even when the rocks themselves have vanished, their influence persists. The chemistry of Earth's mantle, the structure of its crust, the distribution of its minerals, all are legacies of its fiery youth. The iron that runs in our blood once sank toward the core in those early molten days. The oxygen we breathe was once bound in minerals, released slowly through geological processes. Our very bodies are built from elements forged in fire and preserved in science. We are, in a sense, living geology, animated echoes of the planet's first experiments with chemistry. When you hold a rock in your hand, you are holding memory. The smooth pebble worn by water, the jagged shard chipped from a mountain, the glittering crystal in a streambed, each carries within it the history of pressure, heat, and time. To geologists, rocks are not inert objects but storytellers, each grain of mineral a line in a tale billions of years long. Some stories are short, the product of recent volcanic eruptions. Others stretch back into the deep past, to the days when Earth was still glowing with molten fire. There is quiet comfort in knowing that the planet remembers even when we cannot. The skies of Earth's youth have cleared, the seas have calmed, the continents have shifted countless times, but the stones remain. They are the planet's memory keepers, patient and enduring, carrying within them the tale of fire turned to form. And while we may never know every detail, we know enough to glimpse the truth that the fire of Earth's youth is still with us, hidden in the heart of every rock waiting for us to listen. To look at ancient rocks is to look into a mirror of time. They remind us that our planet was once unrecognizable, a world of firestorms and molten seas. They also remind us that out of that chaos came stability, oceans, continents, and life. The fire may have cooled, but its traces remain, etched forever into the stones beneath our feet. Rocks are not just fragments of the earth, they are memory itself, the record of a fiery beginning that shaped everything we know today. Though billions of years have passed since Earth's youth, the fire that once dominated the planet has not gone out. It still burns within, deep beneath the crust, where the mantle churns slowly and relentlessly. Every so often that hidden heat breaks through the surface in a display that reminds us of the world's fiery origins. Volcanoes are, in many ways, echoes of Earth's earliest days, living windows into a time when the entire surface was molten and restless. When lava spurls from a volcano today, it is easy to think of it as a modern event, a sudden disruption to the calm landscapes we know. Yet every eruption is also a memory surfacing, a piece of the planet's ancient character breaking through. The same processes that once covered Earth in magma oceans now create fountains of fire in places like Hawaii, Iceland, and Italy. Though smaller in scale, these eruptions are not different in kind from those that defined Earth's beginning. They are whispers of a time when the whole globe burned. Take Hawaii, for example. The islands sit atop a volcanic hotspot, a place where magma from deep within the mantle rises through the crust. The volcano Kilauea, one of the most active on Earth, has poured rivers of lava across the landscape for centuries. Its fiery flows creep through forests, engulf villages, and build new land as they cool into black basalt. Watching the lava spill into the ocean, sending great clouds of steam into the sky, is to glimpse the kind of spectacle that once dominated the planet. It is destructive, yes, but it is also creative. New land is being born before our eyes, just as the earliest continents once grew from molten stone. Iceland offers another striking reflection of Earth's fiery past. Perched on the mid-Atlantic ridge, where two tectonic plates drift apart, the island is a place where the mantle's heat is never far below. Volcanic eruptions there have reshaped the land repeatedly, sometimes in dramatic fashion. The eruption of Laki in the 18th century poured out enough lava to cover hundreds of square kilometres, releasing clouds of sulphur that dimmed skies across Europe. More recently, eruptions at Eyjafjallajökull and Fagradalsfjall have reminded the world of Iceland's fiery core. And yet, in the midst of this volatility, Iceland thrives. Its geothermal energy powers homes, and its landscapes draw visitors from around the globe. Fire has made it both harsh and beautiful. Other volcanic regions tell similar stories. Mount Etna in Sicily, Stromboli in the Tyrrhenian Sea, Vesuvius looming over Naples, these are places where people live alongside fire, sometimes threatened, sometimes nourished by its presence. Volcanic soils are among the most fertile on Earth, rich in minerals that sustain vineyards, orchards, and fields. The same eruptions that destroy villages can, over decades and centuries, make the land around them flourish. Fire is both destroyer and giver, a reminder that creation and destruction are often two sides of the same coin. Even the seafloor is alive with volcanic echoes. At mid-ocean ridges, lava wells up constantly, creating new crust and spreading the ocean basins apart. These underwater eruptions are rarely seen, but they account for the majority of volcanic activity on Earth. Entire mountain ranges are built in this way, hidden beneath the waves, their peaks stretching across thousands of kilometers. They are proof that Earth's interior is still restless, still shaping the surface as it did billions of years ago. Volcanoes are also storytellers. Their eruptions release gases that remind us of the atmosphere's fiery origins. Carbon dioxide, sulfur, water vapor, and nitrogen. These are the very same gases that once built the first skies, the same breath of Earth that filled the oceans with chemistry. Each plume of smoke is a whisper of that ancient time, a reminder that the planet is still exhaling, still alive. The dual nature of volcanoes, both destructive and creative, is what makes them so captivating. When Mount St. Helens erupted in 1980, it leveled forests, reshaped mountainsides, and darkened skies with ash. The destruction was immense. Yet within years, life returned. Plants sprouted in the ash, animals crept back into the landscape, and the region began to bloom again. In its violence, the volcano had created new opportunities for growth, a cycle that echoes the earliest days of Earth when fire set the stage for water, stone, and life. Volcanoes also connect us directly to the planet's hidden interior. They are the pressure valves of Earth's engine, the points where molten rock and gas escape from deep below. Without them, the planet's heat would remain trapped, perhaps leading to far greater upheavals. Instead, volcanoes allow Earth to release its energy in bursts. Each eruption is both a hazard and a relief, part of the natural rhythm of a planet that is never fully still. In a way, volcanoes are also artists. Their eruptions carve landscapes, paint mountainsides with lava flows, and leave behind sculpted formations of basalt columns, craters, and calderas. Some of the most breathtaking natural wonders on Earth, places like Crater Lake in Oregon or the Blacksand beaches of Iceland, are the direct result of volcanic fire. Their beauty is inseparable from their violence. To stand on such a landscape is to stand on the meeting point of destruction and creation, the ashes of fire reborn as form. It is easy to forget in our daily lives that beneath our feet lies a world of heat. The mantle still churns, the core still glows, and volcanoes are its voice. They are reminders that the fire of Earth's birth has not gone out. It simply lies deeper now, hidden but not gone, ready to emerge in fountains of lava and plumes of ash. Each eruption is not just a geological event but a memory, a message from a planet that has never truly left its molten youth behind. To reflect on volcanoes is to reflect on Earth's dual nature. It is a planet of balance between fire and water, destruction and renewal, chaos and stability. The fiery beginnings of Earth might seem distant, but they live on in every eruption, every plume of smoke, every new island that rises from the sea. Volcanoes are not relics of a past era. They are active participants in the ongoing story of the world. And so, when we look at a volcano today, whether it is the steady glow of lava in Hawaii, the fiery fissures of Iceland, or the towering ash clouds of Vesuvius, we are not only seeing danger, we are seeing the continuity of Earth's history, the persistence of the fire that shaped everything we know. The fire still burns, quietly in the depths and dramatically on the surface, and it will continue to burn for as long as the Earth endures. In their glow we are reminded of where we came from. In their rumble we hear echoes of the molten world that once was. Volcanoes are the planet's memory and its future, proof that fire is not merely destruction but also creation, a force that builds as much as it consumes. The fire of Earth's birth has dimmed, but it has never died. It still breathes, it still shapes, and it still reminds us that beneath the calm surface of the world we know lies the restless heart of a planet that was, and always will be, born of fire. Long before humans learned to smelt ore or polish gemstones, Earth itself was already a master alchemist. The fiery crucible of its youth was not only a display of heat and chaos, but also a vast workshop forging the raw materials that would one day shape civilizations. In the endless churning of magma, minerals crystallized, metals separated, and elements found their places. Out of molten fire, the building blocks of the future were born. The story begins with the differentiation of the young planet. When Earth was still a molten sphere, its heaviest elements, iron and nickel, sank toward the center, creating the dense metallic core. Lighter silicates floated above, forming the mantle and crust. This separation was more than a sorting of weight. It was the foundation of chemical diversity. Elements that preferred to stay in metal gathered below, while those more at home in silicates rose above. In this way, the early Earth organized itself, setting the stage for the minerals and metals that would later emerge. As the mantle convected and magma rose, cooling began to work its magic. Different minerals crystallized at different temperatures, a process known as fractional crystallization. Olivine, with its deep green hue, was among the first to form, followed by pyroxenes, feldspars, and quartz. These minerals, simple in structure yet varied in form, were the alphabet of geology. Layer by layer, they built the crust, each crystal a frozen memory of molten fire. But Earth's alchemy did not stop with silicates. The heat of volcanism concentrated valuable metals as well. Copper, zinc, lead, and gold dispersed in the mantle were carried upward in magma and deposited near the surface. Hydrothermal fluids, heated by volcanic activity, circulated through cracks in the crust, leaching metals from rock and redepositing them in veins. These veins, glittering with ores, would one day be mined by humans to build tools, coins, and machines. Yet long before civilization arrived, they were simply the byproducts of Earth's endless chemistry. Even gems owe their existence to this fiery workshop. Diamonds, formed under immense pressures deep within the mantle, were carried upward by volcanic eruptions known as kimberlite pipes. Crystals like garnet, spinel, and peridot grew in the crucibles of molten rock, later washed into riverbeds or embedded in mountain ranges. What humans would later treasure as symbols of beauty and wealth began as simple expressions of pressure, heat, and chemistry beneath a restless crust. One of Earth's most remarkable tricks was the creation of banded iron formations. Billions of years ago, when oxygen first began to rise in the atmosphere, iron dissolved in the oceans, reacted and precipitated, settling on the seafloor in alternating layers of iron-rich minerals and silica. These formations, born of the interplay between volcanic outgassing seawater and emerging biology, became vast deposits of iron ore. They now supply the steel that builds skyscrapers, ships, and cities. The foundations of modern industry were written into stone by the planet's ancient alchemy. Basalt, one of the most common volcanic rocks, is another reminder of fire's creativity. Though plain to the eye, basalt is a mixture of minerals, plagioclase, pyroxene, and olivine, that carry essential elements like calcium, magnesium, and iron. Weathering of basalt releases these nutrients into soils and oceans, fertilizing ecosystems. In this way, fire forged not only the rocks we stand upon, but also the conditions for life to flourish. Even the food we eat today depends indirectly on the minerals released from volcanic stone. From a human perspective, it is easy to see minerals and metals only as resources. Yet in a broader sense, they are the legacy of Earth's fiery youth. Every coin of copper, every circuit of gold, every diamond in a ring, every beam of steel in a building, all of them began as products of magma, crystallized in the heat of a planet still learning to balance itself. The technologies of civilization are, quite literally, the continuation of Earth's volcanic story. It is worth pausing to reflect on the beauty of this transformation. Fire is so often thought of as a destroyer, and in many ways it is. It burns, it melts, it consumes. But in the heart of Earth, fire was also the great creator. By melting and remelting, by sorting and crystallizing, it brought forth diversity from uniformity. It turned simple elements into complex structures, raw chemistry into glittering minerals. Without fire, Earth would be a barren sphere of stone. With fire, it became a treasure house. To walk across a volcanic landscape is to see this alchemy at work. Black sands glint with fragments of basalt. Green olivine crystals sparkle in lava rocks. Columns of cooled basalt rise like organ pipes, their hexagonal shapes the geometry of cooling magma. Even in their harshness, these places are beautiful, reminders that creation and destruction are inseparable. Each eruption destroys, yet each eruption also leaves behind new minerals, new stones, new gifts for the future. Civilization itself has been shaped by this inheritance. The Bronze Age was made possible by copper and tin, both concentrated by volcanic process. The Iron Age depended on ores forged in the interplay of volcanoes, oceans, and atmosphere. Gold and silver, carried upward by hydrothermal fluids, became the basis of trade and wealth. Diamonds and gemstones adorned crowns and temples, symbols of power created not by humans but by Earth's mantle. The great steps of human history, agriculture, metallurgy, technology, were built upon the materials Earth had prepared long before our species appeared. This perspective gives fire a new kind of dignity. It was not only a force of chaos, but a craftsman, shaping the raw materials of the world with patience and precision. Every eruption was another experiment, every cooling lava flow another set of crystals arranged. Over billions of years, those experiments produced the palette of elements and minerals we now depend upon. Fire was not careless, it was creative, and the alchemy continues. Even today, new minerals form as lava cools, as vents exhale gases into the seas, as rocks are pushed deep into the mantle and transformed under pressure. The Earth has not stopped experimenting. It is still the patient artisan, endlessly reshaping its materials. The jewels we admire and the metals we mine are not relics, but ongoing creations, part of a cycle that will outlast us. To hold a piece of volcanic rock is to hold more than stone. It is to hold the memory of a world once molten, the touch of fire cooled into form, the gift of a planet that knows how to turn chaos into beauty. Every glimmer of crystal, every shimmer of metal, is a reminder that Earth was, and still is, an alchemist. It took the raw ingredients of the cosmos, hydrogen, carbon, iron, silicon, and, through the power of fire, forged them into the materials of mountains, oceans, and life. The story of Earth as an alchemist is, in the end, the story of creation itself. From molten chaos emerged order. From fire emerged stone, from stone emerged the resources that would one day build civilizations. To see the world this way is to recognize that fire is not simply something to be feared. It is also something to be thanked. Without it, there would be no continents to stand on, no metals to work with, no gems to marvel at, no soil to grow our food. Fire, in its patient and relentless way, made it all possible. The fire of Earth's birth still burns in its core, still feeds volcanoes, still shapes minerals in the depths. The planet is still creating, still experimenting, still forging, and as long as it does, the story of Earth the Alchemist continues, a tale of transformation written in stone, metal and crystal, reminding us that from fire comes not only destruction, but also the enduring beauty of creation. For as long as humans have watched flames flicker in the night or seen volcanoes send rivers of fire down mountainsides, they have told stories about fire. To early peoples, it was not simply a chemical reaction or molten rock. It was life, power, danger, and mystery. Fire gave warmth and cooked food, but it also burned fields and destroyed villages. Volcanoes enriched soils yet buried cities. No wonder so many cultures wove myths around fire, seeing in it both the origins of creation and the threats of destruction. In those myths, we glimpse humanity's deep connection to Earth's fiery past. In Greek mythology, fire was the gift that set humans apart from the animals. According to the legend, it was stolen from the gods by Prometheus, a titan who defied Zeus by carrying flame down to mortals hidden in a fennel stalk. With fire came cooking, metallurgy, and civilization itself. But such a gift was dangerous, and Zeus punished Prometheus by chaining him to a rock where an eagle devoured his liver each day, only for it to grow back overnight. It is a grim tale, yet at its heart is recognition of fire as both liberating and perilous, a force that elevates humanity even as it threatens to consume it. Far from Greece, on the islands of Polynesia, fire was also given divine form. In Hawaiian tradition, Pele, the goddess of volcanoes, is both a creator and a destroyer. She shapes the islands with her molten flows, making new land rise from the sea. Yet she also brings devastation when lava engulfs villages. To this day, stories of Pele accompany eruptions in Hawaii, reminding residents that the land they live upon was born of fire. The myths are not just tales of capricious gods, but living acknowledgements of Earth's volcanic heartbeat. In the myths of the Maori of New Zealand, fire was brought to the world by the demigod Maui, who obtained it from the fingernails of the goddess Mahuika. Each nail burned with flame, and when Maui tricked her into giving them all away, the last nail set fire to the land itself. In the ashes of that conflagration, Maui preserved fire within certain trees, teaching humanity how to kindle it by rubbing sticks together. The story blends myth with practical truth. Fire was indeed hidden in wood, waiting to be coaxed out by friction. Here, myth preserved memory and skill alike. Across the world, indigenous Australian traditions tell of fire as both sacred and transformative. In many Dreamtime stories, ancestral beings brought fire to the land, shaping its landscapes and teaching people its use. Some stories describe how fire was stolen from spirits or animals, echoing the theme of fire as a gift not freely given but won through struggle. These tales often carry moral lessons about respect for fire, warning against carelessness with a force that could bring both survival and ruin. The dual nature of fire as creator and destroyer is nearly universal. In Hindu tradition, the god Agni embodies fire, both the flame of sacrifice and the consuming blaze of destruction. Fire is the mouth of the gods carrying offerings upward in Timok, yet it is also a reminder of impermanence, reducing everything to ash. In Zoroastrianism, fire represents purity and truth, an eternal flame kept burning in temples as a symbol of divine order. In each case, fire is not just a tool but a bridge between humans and the divine, between the material and the spiritual. Volcanoes, too, inspired their own myths. In Japan, the sacred Mount Fuji has long been revered, its eruptions seen as expressions of divine will. Among the Romans, the god Vulcan gave his name to volcanoes, imagined as the great forge beneath the earth, where weapons and tools for the gods were crafted. To the ancient Romans living near Mount Vesuvius, it was no stretch to imagine that the roaring mountain was a literal forge of divine fire. The catastrophic eruption that buried Pompeii only reinforced the awe and terror such mountains commanded. In Norse mythology, the cosmos itself begins and ends with fire. At the dawn of time, flames from the realm of Muspelheim met the ice of Niflheim, and from their union the first beings were born. At the end of days, during Ragnarok, fire will sweep across the world, consuming gods and mortals alike, leaving only the possibility of renewal. Here, fire is the eternal cycle of creation and destruction, echoing the same balance that shaped Earth's geology. Fire builds, fire destroys, and from destruction comes rebirth. The persistence of these myths across cultures is telling. They arise from observation of the natural world, volcanoes that erupt without warning, lightning that sparks wildfires, lava that creates new land even as it destroys the old. To ancient peoples, such forces were incomprehensible in purely physical terms. Myths gave them meaning, wrapped chaos in story, and explained why the earth breathed fire. Even today, though science offers detailed explanations, the myths retain their resonance. They speak to something deeper than geology, the human need to understand, to place ourselves in a world that often feels both generous and hostile. What makes these myths especially poignant is how closely they mirror real history. Prometheus stealing fire from the gods is, in essence, a story about humanity learning to control flames. Archaeological evidence suggests humans were using fire over 1 million years ago, long before civilization, and the mastery of fire indeed changed everything. It allowed for cooking, which unlocked more nutrients from food. It provided warmth, enabling people to survive in colder climates. It offered protection from predators and a gathering place for community. Fire was not just another discovery, it was the spark that ignited culture itself. Similarly, the myths of volcano gods and goddesses reflect an intuitive understanding of how land is made. Pele creating islands from lava mirrors the geological reality that Hawaii is indeed born from volcanic eruptions. The Maori story of fire hidden in trees reflects the real-world technique of fire-making. Norse myths of fire and ice shaping the world echo the actual interplay of volcanism and glaciation in northern landscapes. The myths may cloak these truths in divine characters, but beneath them lies a profound observation of nature. There is also a universality to how humans see fire, as both gift and punishment. The same flame that cooks food can burn a village. The same volcano that creates fertile soils can bury them under ash. Myths captured this ambiguity, teaching respect for a force that is never entirely safe, never entirely tame. In this sense, fire was a teacher as much as it was a danger. When we connect these myths to Earth's fiery history, the continuity becomes clear. The planet's earliest days were dominated by fire, by lava rivers, and by an atmosphere thick with volcanic gases. Though humans were not there to witness it, the echoes of that fiery past live on in the volcanoes and flames we still see today. Myths arose as our ancestors sought to explain those echoes, to make sense of fire's presence in their lives. They may not have known about magma oceans or mantle convection, but they knew that fire was both necessary and dangerous, both divine and destructive. In their own way, they were telling the same story geologists now tell with rocks and isotopes. Earth was, and still is, a planet of fire. To reflect on these myths is to see humanity's imagination braided with the planet's reality. Prometheus, Pele, Agni, Vulcan, all are characters in a timeless drama about creation and destruction. They remind us that fire is not just a tool or a hazard, but a presence woven into our very identity. We are children of fire, shaped by it from the planet's birth to our own mastery of it. And so the myths endure, not just as relics of superstition, but as living metaphors. They link us to our ancestors, to the land beneath our feet, and to the fiery heart still beating within Earth. Fire, whether in a campfire's glow or a volcano's roar, continues to inspire both awe and respect. It is both ancient and immediate, both scientific and mythical, and in every story, whether of gods gifting flame or mountains exhaling lava, we hear the same truth. Fire is the beginning, fire is the end, and fire is the thread that binds the story of Earth and humanity together. If Earth's fiery youth was a story of transformation, then Venus is its cautionary twin. The two planets began in much the same way, similar in size, similar in mass, forged from the same ingredients swirling in the solar nebula. Both were wrapped in thick atmospheres of carbon dioxide and water vapour. Both endured volcanic eruptions that reshaped their crusts. Both glowed with heat in their infancy. Yet while Earth slowly cooled, clearing its skies and filling its oceans, Venus never escaped its furnace. Today, Earth is a blue and green world, teeming with life, while Venus is a suffocating oven where lead would melt and the skies are forever shrouded in acid clouds. To compare them is to see how delicate the balance of habitability truly is. The first great difference between Earth and Venus was distance. Venus orbits closer to the Sun, about 30% nearer than Earth. That difference meant slightly more solar energy, which in turn made it harder for Venus to cool. In the early days, when both planets were wrapped in thick steam atmospheres, Earth was just far enough away that water vapour could eventually condense into oceans. Venus, by contrast, was too hot. It steamed and lingered in the atmosphere, refusing to fall as rain. Without liquid water, Venus could not draw down carbon dioxide into rocks, a process that on Earth slowly reduced the greenhouse effect. Instead, its atmosphere grew ever thicker, trapping more heat in a runaway spiral. On Earth, the carbon cycle became a planetary thermostat. Rain pulled carbon dioxide from the air, rivers carried it into oceans, and the gas was locked away in carbonate rocks on the seafloor. Volcanism released carbon dioxide back into the skies, but the balance held steady over time. This delicate exchange allowed Earth to cool and stabilize. Venus had no such cycle. With no oceans to act as sinks, its carbon dioxide simply accumulated, building an atmosphere more than 90 times thicker than Earth's. The result was a greenhouse effect so extreme that the surface temperature soared above 400 degrees Celsius, hotter than the surface of Mercury, even though Mercury is closer to the Sun. Volcanism on Venus also played its part. Like Earth, Venus has a restless mantle that constantly pushes heat upward. But on Venus, with no plate tectonics to recycle the crust, lava spread across enormous plains in periodic cataclysms. Instead of small, steady eruptions like those on Earth, Venus appears to have undergone global resurfacing events where entire regions were drowned in molten rock. These eruptions pumped even more carbon dioxide into the skies, thickening the greenhouse blanket. The land was reshaped again and again, but the heat never left. Fire, instead of balancing with water, only reinforced the planet's suffocating destiny. The presence of Earth's moon may also have been a quiet advantage. The moon helps stabilize Earth's tilt, preventing wild swings in climate that might have hindered the long-term persistence of oceans. Venus, without such a stabilizer, may have experienced more chaotic shifts. Some scientists suggest that Venus could once have had shallow seas, but instability in its atmosphere and tilt, combined with its closeness to the Sun, eventually boiled them away. Once the water was gone, the planet crossed a threshold from which there was no return. To stand on Venus today, if it were possible, would be to step into a vision of Earth's past gone wrong. The surface is a rocky desert dotted with volcanic domes and lava plains, but it is hidden beneath a thick yellow atmosphere. The pressure is crushing, like standing nearly a kilometre under Earth's oceans, and the heat is intense enough to melt metals. Clouds above are made not of water but of sulfuric acid, drifting in layers that reflect sunlight and hide the surface from view. The winds in the upper atmosphere race at hurricane speeds, yet near the ground the air is nearly still, oppressive and heavy. It is a world where fire never yielded, where water never took hold, where the cooling never came. The contrast with Earth could hardly be sharper. Oceans here cover most of the surface, moderating climate, nurturing life and storing carbon. The skies are blue, clear enough for sunlight to reach the ground without being smothered by haze. Temperatures vary, but they hover in ranges that allow liquid water to persist. Instead of a static, suffocating crust, Earth has dynamic tectonics. Continents drift, plates recycle, volcanoes vent heat in manageable bursts. This mobility helps regulate the planet's temperature over deep time, preventing the kind of runaway heating that consumed Venus. The lesson is gentle yet profound. Small differences can shape planetary destinies. A few million kilometers closer to the Sun, and Earth might have been another Venus, smothered by steam and stripped of oceans. Without the balance of the carbon cycle, Earth might have suffocated beneath its own greenhouse blanket. Without plate tectonics or a stabilizing moon, climates might have swung too wildly for stability. That Earth cooled while Venus burned is not inevitable but contingent, the outcome of many factors aligning just so. In this way, Venus is both a warning and a mirror. It shows us what happens when the balance tips too far toward fire, when heat is trapped faster than it can escape, when oceans never form to soften the planet's breath. It is not that Venus was doomed from the start, it likely shared many of Earth's early conditions, but that the scales tilted, and once they did, there was no turning back. And yet Venus also helps us appreciate Earth's fortune. When we look up and see a blue sky, when we watch waves break on a shoreline, we are witnessing the results of a balance struck billions of years ago. Earth found the narrow path between fire and ice, between too much greenhouse and too little. That path is what allowed seas to form, continents to rise, and life to flourish. Venus, by contrast, shows how easily a world can become uninhabitable, not because it lacks ingredients, but because its systems never found equilibrium. The two planets together tell a cosmic story. They remind us that habitability is fragile, that the conditions we take for granted are the result of delicate balances. Fire and water, distance and chemistry, tectonics and atmosphere, all must play their parts in harmony. Tilt the balance and a blue world can become a furnace. Maintain it and a furnace can cool into a cradle for life. There is a quiet humility in this lesson. We live on a planet that has walked the tightrope of habitability for billions of years. Its balance is not guaranteed, not permanent, but maintained by natural cycles that could easily have tipped another way. Venus stands nearby in the sky, a bright and beautiful star to our eyes. But its beauty hides a truth. It is the road Earth might have taken. To remember this is to cherish the balance we enjoy, to understand that the blue skies and calm seas are gifts of circumstance as much as inevitability. In the tale of two planets, Earth and Venus, we see both contrast and kinship. Born of the same nebula, shaped by the same fire, they parted ways because of distance, water, and balance. One cooled, one burned, one became a cradle, one remained a furnace. Together they remind us that life exists not because the universe is always kind, but because sometimes, just sometimes, the balances hold. And when they do, a fiery world can soften into blue. For most of human history, people have chosen to live close to fire. Not campfires alone, but the great fires of the earth itself, volcanoes rising above fertile plains, their slopes dotted with villages, fields, and later cities. At first glance, this seems like folly. Why build homes at the feet of mountains that can bury them in ash, scorch them with lava, or shake them with earthquakes? And yet, again and again, humanity has returned to live in the shadow of fire. The answer lies in the strange and enduring relationship we have with Earth's fiery heart, one of danger and destruction, but also of fertility, beauty, and belonging. Volcanoes are paradoxical neighbours. When they sleep, their soils are some of the richest on the planet. Eruptions break down rocks into mineral-rich ash that weathers into fertile ground. Farmers who plant their crops in volcanic soil often find their fields bursting with productivity, yielding grains, fruits, and vegetables in abundance. The slopes of Mount Vesuvius are covered with vineyards and orchards. The fields around Mount Etna in Sicily produce citrus groves that thrive in the volcanic soil. In Indonesia, rice terraces spread across volcanic plains, nourished by minerals released from eruptions centuries ago. Fire destroys, but in time fire feeds. This cycle of danger and renewal has tethered people to volcanoes across the globe. Consider the city of Naples, nestled beside Vesuvius, the same volcano that buried Pompeii nearly 2,000 years ago. Despite the memory of that destruction, people never truly abandoned the land. They returned, drawn by its richness, its beauty, and perhaps even its defiance. To live there is to accept that fire may one day awaken again. In Hawaii, communities have long lived with the constant presence of volcanic activity. Kilauea has flowed repeatedly in modern times, swallowing houses and forests with rivers of molten rock. Yet people still build homes on its flanks. The land is sacred, created by Pele, the goddess of fire. To live there is not only to risk destruction, but also to embrace a deep cultural connection to the origins of the islands themselves. Fire is not just a hazard, it is home, part of the identity of the land and its people. In Iceland too, fire and life intertwine. The island sits astride the mid-Atlantic ridge, and eruptions are frequent. The eruption of Eyjafjallajökull in 2010 sent plumes of ash into the skies, grounding flights across Europe. Yet Icelanders do not flee from their fiery home. Instead, they have learned to harness it. Geothermal energy drawn from the heat of the earth powers homes, heats water, and sustains greenhouses that grow food in an otherwise harsh climate. Fire is no longer just a threat but a resource, a steady companion that provides warmth in the cold North Atlantic. The story is similar elsewhere. Around Mount Fuji in Japan, villages and temples have long stood in its shadow, even though the mountain has erupted repeatedly in recorded history. In Central America, Guatemala's volcanoes rise above fields of maize and coffee plantations. In East Africa, volcanic soils sustain crops that feed millions. Time and again, humans choose to live where fire sleeps lightly beneath the surface. The coexistence is not without cost. When volcanoes awaken, their fury is swift. Pyroclastic flows, avalanches of gas and ash moving faster than a sprinting horse, have buried entire towns in moments. Lava flows have consumed villages stone by stone, their glowing fronts unstoppable. Ash clouds blot out the sun, collapsing roofs with their weight and choking the air. Lakes near volcanoes can even turn deadly, as with Lake Nyos in Cameroon, where a sudden release of carbon dioxide suffocated thousands in a single night. To live with fire is to live with risk, a truth that has marked human history as long as we have farmed its fertile soils. Yet for all the destruction, fire is rarely only feared. It is also revered. In many cultures, volcanoes are sacred, places where gods dwell or where the earth itself seems alive. They command respect and inspire awe. Even when they erupt, people often return to rebuild, not only because the land is fertile, but because it is part of who they are. The fire beneath their feet is woven into their sense of place and belonging. There is also a strange comfort in volcanoes. They are reminders that Earth is alive, that it still breathes and moves beneath its crust. Their eruptions may terrify, but they also connect us to the planet's earliest days, when the entire world was molten and fiery. To watch lava flow today is to glimpse in miniature what once defined the whole Earth. It is like seeing a memory surface, a fragment of our planet's youth returning to remind us of its past. The relationship is therefore more than practical, it is poetic. Fire and humanity share a long companionship. We tamed flames to cook, to forge tools, to gather in warmth. Living near volcanoes is an extension of that same intimacy, only on a planetary scale. We take the gifts of volcanic soils, geothermal warmth, and minerals, and in return we accept the risks. It is a pact written not in words but in lives lived at the edge of fire. To imagine life in such places is to understand resilience. Farmers planting crops in the shadow of Etna do so knowing that their fields may one day vanish beneath ash. Families in Hawaii rebuild their homes on land that may again be swallowed by lava. In Iceland, communities adapt to eruptions that reshape their island. This resilience is not blind optimism, but a recognition of the cycles of Earth itself. Fire destroys, fire creates, and life endures in the balance. From above, volcanic regions look almost serene. Cones rise against skies, their slopes green with fields and forests. Towns nestle in valleys, unaware to the casual eye of the restless heat beneath. But beneath that calm lies constant motion. Magma rising and falling, gases building, pressures shifting. The fire is always there, waiting, reminding us that we live not on a static rock, but on a living, breathing planet. To live with fire today is to participate in Earth's ongoing story. It is to acknowledge that the planet's fiery past is not gone, but continues in eruptions and earthquakes. It is to accept that danger and fertility are bound together, that the same processes that feed us can also destroy us. It is to see fire not only as a hazard, but as a companion, shaping landscapes, nourishing soils, and connecting us to the deep memory of the earth. There is a quiet beauty in this coexistence. To stand on the slopes of a volcano at sunset, watching the glow of lava against a darkening sky, is to feel the ancientness of the world. To walk through vineyards grown in volcanic soil is to taste the gifts of fire transformed into sweetness. To soak in a hot spring heated by magma deep below is to rest in the warmth of a planet that still breathes. Fire in these moments is not an enemy, but a reminder that Earth itself is alive. In the end, humanity's strange relationship with volcanoes reflects something about us as well as about the planet. We are drawn to fire, both fascinated and humbled by it. We build in its shadow, reap its benefits, endure its wrath, and return even after disaster. Fire shaped the Earth, and in a quieter way it shapes us too. It reminds us of fragility, of resilience, of the thin line between destruction and creation. To live with fire today is to live with Earth itself, to accept the planet as it is, restless, unpredictable, but also generous. Fire feeds the soil, powers our homes, and teaches us respect for forces greater than ourselves. And in that fiery companionship, humanity finds not only danger, but also belonging. For fire is not merely beneath our feet. It has always been, and always will be, part of our home. The story of Earth begins in fire, yet it does not end there. What began as a molten sphere of chaos slowly transformed into a cradle capable of nurturing life. It is a tale of extremes, from magma oceans to blue seas, from fiery skies to breathable air, from barren stone to living ecosystems. To trace this arc is to follow one of the most remarkable transformations in the cosmos, the turning of lava into life's home. In its earliest days, Earth was unrecognizable. The surface glowed with liquid rock, waves of magma rolled across the planet, and the skies were filled with smoke and steam. The young world radiated its heat into the cold of space, glowing like a dying ember. The crust that formed was thin and fragile, constantly broken apart by rising magma or shattered by impacts from space. To imagine such a world is to imagine a planet raw and violent, a place where survival as we know it would have been impossible. And yet even in this chaos the seeds of stability were already being sown. As the planet cooled, raindrops began to fall, hissing into steam as they struck the hot crust. Over countless years the rains persisted, carving channels, filling basins and pooling into the first oceans. Comets and asteroids brought even more water, adding to the deluge. What began as vapour in the skies became seas spread across the surface. Fire had built the planet, but water began to soften it. The arrival of oceans marked the first great transformation. They were not calm and blue as they are today, but hot, mineral-rich, and steaming with energy. Into them poured gases from countless volcanic eruptions, carbon dioxide, methane, nitrogen, and sulfur. Hydrothermal vents bubbled at the seafloor, carrying heat and minerals upward into the water. Lightning flashed across the skies, splitting molecules and sparking new chemical bonds. In this turbulent mixture, simple compounds formed, molecules that carried the first whispers of biology. Here, the story of fire takes a new shape. Volcanoes did not merely burn and destroy, they exhaled the gases that filled the seas with chemistry. The minerals they released became the raw ingredients of life. The vents they created provided the energy gradients needed to drive reaction. Fire was no longer just the builder of stone, it was also the hidden partner in the birth of biology. Without fire, there might have been no atmosphere, no oceans, no chemistry rich enough to cross the boundary into life. The leap from chemistry to biology was slow and subtle, more like a series of whispers than a sudden shout. Simple molecules assembled into more complex ones. Lipids formed membranes, creating tiny bubbles where reactions could take place. Amino acids linked into peptides and nucleotides into strands of RNA. These early structures were fragile, easily broken apart, but some endured long enough to copy themselves, to evolve, to compete. From the fire-fed oceans, the first living cells arose. They were small, invisible to the eye, yet they carried the spark of something new, the ability to persist and change. Life, once it appeared, began to alter the planet in return. Microbes consumed gases, released others, and reshaped the chemistry of the seas and skies. The atmosphere, once suffocating, slowly transformed. Oxygen would not arrive in significant amounts for billions of years, But even before then, life had already begun to weave itself into Earth's systems. The cycle had closed. Fire built the world, water softened it, and life transformed it. Looking back across this arc, the fragility of it all is striking. A small shift in distance from the sun, and Earth might have boiled away like Venus. A thicker crust, and volcanic gases might never have escaped to form an atmosphere. A less steady rainfall, and oceans might not have gathered. The conditions that allowed life to take hold were not inevitable, but balanced on a razor's edge. Yet the balance held. Fire, water, and time worked together, and the improbable became real. There is also resilience in the story. Life did not emerge in a gentle garden, but in a cauldron of storms, eruptions, and impacts. It was tested from the very beginning, forged in environments of heat and pressure. That resilience is still with us today, written into the tenacity of microbes that thrive in boiling springs, acidic lakes, and deep ocean vents. In their persistence, they carry memory of the world from which all life emerged, a world of fire turned fertile. The transformation of Earth is more than a geological tale. It is a reminder of the patience of nature. Billions of years of cooling, raining, erupting, and reacting were required before seas could settle and life could begin. The Earth that seems so steady beneath our feet is the product of endless change. A planet sculpted by both violence and calm. To see a blue sky, to walk along a shoreline, to breathe in air rich with oxygen is to witness the outcome of that transformation. Every breath and every wave is part of the legacy of fire turned to life. Even today, the memory of Earth's fiery beginning is never far away. Volcanoes still erupt, sending lava into the seas. Lightning still cracks across stormy skies, splitting molecules as it did billions of years ago. Hydrothermal vents still bubble at the seafloor, nurturing ecosystems that remind us of life's earliest cradles. The planet still carries its fire, hidden in its core, breathing it out in plumes and eruptions. Fire did not vanish when life began, it became part of life's story, and perhaps that is the most poetic truth of all. The same forces that once seemed hostile and destructive were the very ones that made life possible. Fire, water, and stone conspired to build not only a planet but a home. What began as chaos ended as balance. What began as lava became life's cradle. To reflect on this journey is to see Earth not as static but as alive, not as accidental but as enduring. The oceans we know today are ancient gifts, poured from the skies and delivered from space, filled with the chemistry of fire. The rocks we walk upon are the cooled remains of molten rivers that once covered the world. The air we breathe is the descendant of volcanic exhalations, altered and refined by life itself. Everything around us carries the memory of that transformation. The story closes in a circle. From fire came stone, from stone came seas, from seas came life. The world that began as a glowing sphere of magma became the blue planet, the cradle of countless living forms. The fragility of that balance is profound, yet it is also enduring. Fire still burns, oceans still flow, life still thrives. To live on Earth is to dwell within that circle, to be part of the arc from lava to life. In the end, the story of Earth's fiery youth is not one of destruction alone, but of transformation. Fire was the beginning, but not the end. It was the first step in a journey that led to seas, skies, and life itself. The world that once blazed like a star has become a home, a place of forests and rivers, of creatures and people, of endless possibility. Fire made this possible, and its legacy endures in every stone, every drop of water, every breath. From lava to life's cradle, Earth's story is one of fragility, resilience, and wonder. It is a story still unfolding, written not only in the rocks and oceans, but in us, the children of a planet that was born in fire and learned with time to nurture life. In the beginning there was fire, Not the comforting glow of a hearth or the flicker of a torch, but fire on a planetary scale. Oceans of molten rock, skies thick with smoke, and a crust so thin and fragile that it cracked and boiled with every breath of the young Earth. The world was not yet the familiar blue and green sphere we know, but a place caught between the violence of its birth and the possibility of its future. Over billions of years that furnace changed. The fiery rivers hardened into rock, rain fell in torrents to carve seas, and the smoke-choked skies began to clear. The transformation was not quick, nor was it gentle. It was the work of time itself, of balance found between heat and cold, between destruction and renewal. What began as chaos became calm. What began as fire became water. What began as inhospitable became a home. This is the story we have traced. From the first cloud of dust that coalesced into a planet through the magma oceans, the bombardments from space, and the endless exhalations of volcanoes. Each chapter has been a reminder that Earth is not static but alive, reshaped again and again by the forces within it. Fire, which seemed at first only a destroyer, proved to be a creator. It gave us our minerals and metals, our continents and soils, and the chemistry that made life itself possible. The rains, too, were children of fire. Steam released from volcanic throats rose into the atmosphere and fell back to the surface as the first raindrops. They hissed against lava, boiled away in clouds of steam, but they returned again and again till they filled the basins and created oceans. Those seas, turbulent and mineral-rich, became laboratories where fire's ingredients mixed with water's stability. It was here that molecules learned to link together, to persist, to replicate. From the cauldron of fire and water came the first spark of biology. Once life appeared, it began to change everything in turn. The gases exhaled by volcanoes were reshaped by microbes into oxygen, altering the atmosphere forever. Sediments from rivers hardened into rocks that preserved the story of these changes. Continents, lifted by tectonic movements, broke apart and rejoined, creating landscapes where life diversified. And through it all, the fire within Earth never truly went out. It still burns in the core, it still rises through cracks in the crust, it still bursts forth in eruptions that remind us of the world's molten youth. The contrast between Earth and its planetary sibling, Venus, shows how delicate this balance truly was. A little closer to the sun, and Earth might have remained a furnace, its oceans never condensing, its skies forever suffocating. Instead, our planet cooled just enough, balanced itself just enough to become a cradle. The difference between a home and a wasteland was only a matter of chemistry, distance, and time. That Earth found its way to balance is both a scientific fact and a quiet wonder. Throughout history, humans have lived with fire, both mastering it and fearing it. We told stories about Prometheus stealing flame, about Pele shaping islands, about gods who breathed fire as both punishment and gift. Our myths were born from the same awe we feel standing near a volcano today, watching lava carve the land anew. Those stories are not just legends, but reflections of a truth. Fire has always been part of us. It gave us light, warmth, and civilization, just as it once gave the Earth its oceans and its atmosphere. To live on Earth is to live with that inheritance. The soils that feed us are enriched by the volcanic ash. The metals we forge into tools and machines were concentrated by ancient magma. The gemstones we prize formed under the crushing pressures of fire's depths. Even our very existence, every breath we take, depends on the atmosphere that volcanism once exhaled. Fire is not behind us, it is within us, in the iron of our blood and the oxygen we breathe. And yet it is the gentler face of Earth that defines our experience now. The blue skies, the flowing seas, the continents that hold forests, rivers, and plains. These are the gifts of fire transformed into calm. It is easy to forget that beneath every quiet shoreline lies a history of firestorms, that beneath every tranquil field lies rock once molten and raw. The Earth we know is not separate from its fiery past, but built upon it. There is fragility in this story. Small changes in balance could have led elsewhere. Too much heat and water would have been lost, too little and the world might have frozen. Yet there is also resilience. Fire, water and stone endured long enough to create conditions for life, and life proved strong enough to shape the planet further. Earth's journey was not inevitable, but it was possible, and possibility was enough. As we reflect on this transformation, there is a quiet poetry in how the circle closes. From fire came oceans, from oceans came life, and from life came creatures capable of asking how it all began. We, the descendants of that transformation, now look back across billions of years and see the arc of a story written in stone and sea. The molten rivers are gone, but their legacy is everywhere, beneath our feet, within our breath, and in the very questions we ask about our origins. Perhaps that is the most extraordinary gift of Earth's fiery past. It did not only create continents, oceans, and life, it also created minds able to wonder, to trace history from rocks, to imagine magma oceans and steaming skies, to see ourselves as part of a planet's great unfolding. Fire gave us not only the conditions to live, but the chance to reflect on what it means to live at all. And so the story closes softly. From chaos came calm, from fire came water, from stone came life. The earth that once blazed like a star has become a cradle, fragile yet enduring, fierce yet nurturing. Its fiery past gave us oceans, continents, life, and the ability to look back in awe, to wonder how a world born of lava became the home we know today. That is the gift of fire. It is not only destruction, but transformation. It is not only chaos, but creation. It is not only history, but memory. And it is a memory that lingers in every stone, every wave, every breath, reminding us that we live upon a planet that was born in fire and learned, with patience and time, how to hold life in its hands.